Okay, let's do some math for fun. Today, I have the Laplace Transform marathon for you guys. We have a total of 24 of them. And of course, here's the file. You guys can go ahead and download that. Please see the description for the file and the notes, and also the timestamps for your convenience. And here is the definition of the Laplace transform. As you can see, it's just an improper integral, and you have e to the negative st times the function right here, and hopefully it converges. And to guarantee that this right here converges, you just have to make sure that f of t has exponential order. What that means is that f of t cannot be too big. The idea is you can just think about it. If you have e to the positive t squared, in that case, that will make this improper integral diverge, right? So you just have to make sure that happens. And if you ever wonder why Laplace transform can help you solve differential equations, go ahead and check out mu prime math's video. I will have that link in the description for you as well. Man, that video was so good because I actually have never seen that before when I was taking Laplace transforms back in the days. I mean, taking the differential equation class back in the days. All right, so now, here we go. This right here is the first one, and of course, we'll be doing a lot of proofs. So, here we go. Laplace transform of e to the at, well, that's the integral from 0 to infinity, and we'll just use this formula. So, we have e to the negative st times e to the at, and then dt. So you just apply that definition, and in the end, we're just going to be working on a lot of integrals, pretty much. All right, so now, base right here and here, they are just e, so it's good. We can just integrate this from 0 to infinity, and we can just combine this as a minus s, yeah? So I'll just write it as a minus s, and then I will factor out the t right here, and then I will have the dt right here. So now, to handle this improper integral, you should technically take the limit, and then you can say b goes to infinity, and then the integral goes from 0 to infinity, all that stuff. But in this video, I'm just going to skip that. I will just write down the infinity symbol. You just have to remember we will be taking limits. Okay, here we go. To do this, first, of course, just note your integration. This is just e to a number times t to the first power. So the integral of this is just e to the a minus s t, but remember the Lu chain, the reverse chain rule, right? The derivative of this is just that. When we're doing the integral, be sure to divide it by that. So we will have to do 1 over a minus s. So that's the integral part. And then we will have to plug in from 0 to infinity and all that stuff. Now, here is the deal. When we plug in infinity to the t, you will see that we'll end up with something like this. 1 over a minus s, and then e to the a minus s. And here you have positive infinity, right? And then minus, and again, I know this is a bad notation, but as I said, it's just a shorthand notation. It's still okay, yeah? Just remember we're taking limits. And then you put 0 in here, so we have 1 over a minus s, and then we have e to the a minus s times 0, like this. Right? So that's the first part, and this is the second part. And now here is the deal. In order for this right here to converge, we have to make sure e to this power actually end up to be 0. Because we have infinity times this already, the idea is that we need to make sure this part has to be negative. And in order for this to be negative, of course, that means I will have to have a minus s to be less than 0. And of course, we can solve this inequality, move the s to the other side, meaning that s has to be bigger than a. We need to have this condition here in order to make this negative, so that you can see we will have e to the negative infinity, and then that will be 0, times all this, that will be 0. So, with this condition, we will see that the first part is just nicely equal to 0, and then the second part will just minus, and you see this is just 1 over a minus s, and then e to the 0 power right here is just 1. So we just have this right here. And finally, what we can do is we can also just distribute the negative here and here, meaning you just switch the order, so you get 1 over s minus a, like this. So this right here is it. And again, after you finish all that, you should technically include this condition. So you will have to say s should be greater than a. Right? So that's it. That's it, that's it, that's it. Very good, huh? That's the first one. Not so bad. All right, so now continue. And we'll be using this for the next few. So look at this, right? Look at this. Okay. So again, how are you guys doing? Let me know. Leave a comment down below. Let me know. I'm doing okay and doing lots of math lately. How about you guys? And hopefully everybody is doing well, of course. Stay safe, stay healthy. All right, number 2 right here. And of course, I'll be doing this in order in the sense that one is based on the other, blah, 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 right? So here is the second one. We'll be doing the power function instead. So we have this. Our goal is to get the Laplace transform of t to the nth power. And here, I'm going to assume that n is just a non-negative whole number, right? So I want to know what this is. And I would like to have n is 0, 1, 2, so on, so on, so on. And in fact, later on, we can actually extend this to like some like real numbers such as n is equal to 1/2. But that will be for question number 23. So not now. Okay, this is how you can do it. First, you can use the definition. So you can put the t to the nth power right here instead, right? And you can just work that out. And you can use integration by parts n times. And actually, technically, you have to do that a lot of times. And then you have to do a lot of math. Or you can do the following. Check this out. This is how we are going to do it. I will use this right here to help us out. So have a look right here. We know the Laplace of e to the at is equal to that. And if you have e to the at, in fact, we know the series expansion for that, isn't it? So I will write this down right here for you guys. So this is how we are going to do it. So notice that we have this already, the Laplace transform e to the at, which we know this is equal to 1 over s minus a, like this. And in this particular case, I'm going to choose a to be greater than 0. I can choose whatever a that I want. I can say Laplace of e to the whatever positive a times t, right? So of course, this is still legit. However, you still have to include this condition. So you just have to make sure that both s and a are greater than 0. So that's pretty much what I have. And again, I mentioned about the series. We know how to handle the series right here. So I write this down. Recall. Let me just put down recall. And I will just put this down right here for you guys. E to the x power. This is just the power series expansion for e to the x. This is the series as n goes from 0 to infinity. And we have x to the nth power over n factorial. And if you would like to recall and review your series, you can check out my power series marathon for you guys, right? So that's what we have. And this right here is true for all x. So let me also just write that down right here. So what we are going to do is, you see here we have e to the at. So let's go ahead and just focus on this part first. So when I have e to the at, all I have to do is just put the at into this x right here. And this is legit because it's true for all the inputs. So I can just open the parentheses with at inside raised to the nth power over n factorial like that. So that's pretty nice. And of course, you can just work out this right here a little bit. And you see this is the series as n goes from 0 to infinity. And this is how I'm going to do it. I will put down t to the nth power first, like this, over n factorial. And then we have a to the nth power, like that. So this is what we have. All right? Okay, then another thing I want to do is, let's look at this part. And I will just do a little divider here. Well, we have 1 over something. So recall that 1 over 1 minus x. Yes, this is our best friend. This right here is equal to the sum as n goes from 0 to infinity, just x to the nth power, like this. However, this is only true if the absolute value of x is less than 1, right? So be really careful on this right here. However, it's actually not so bad at all. Now, let's look at the series expansion for this. So we have 1 over s minus a, like this, yeah? Well, in order for us to use this, we actually have to have a 1 right here, but this right here is an s. That's no good. But it's okay because we can factor out the s. So it looks like we have 1 over s times 1 over, I factor out the s, so we have 1 right here, and then I factor out the s, so we have minus a over s like this. And of course, you can put down parentheses like that. Now, here is the deal. Because we do have this condition, have a look. S is greater than a, and they are both positive, and right here we have a over s. So of course, in this case here, notice that the absolute value of a over s, the top is smaller than the bottom, right? This right here has to be less than 1, for sure. So, with that said, we know we can use our best friend right here. In the front though, we still have 1 over s, and then right here, we can put this into here, so we have the series as n goes from 0 to infinity, and we just need to write this down in here, so open the parentheses with a over s, and then raised to the nth power, like that. Right? So that's pretty much it. And now I'm just going to erase this, and then we will see how we can make the connection between one and the other. Okay. Of course, maybe let's simplify this a little bit actually. So this right here, I will have the summation. N goes from 0 to infinity. On the top, we have a to the nth power, but let me put that aside like this, a to the nth power. On the bottom, we have s to the nth power, but we have another 1 on the bottom as well. So all in all, we have 1 over s to the n plus 1, like that. Okay, now have a look right here. This is true that we know. So here is the deal. Let's go ahead. Instead of looking at the e to the at, and also this, have a look. E to the at is nicely equal to this, isn't it? Yes, it is. So I can just actually put that down right there. So we have the Laplace transform, and actually let me put this down in blue. We have the sum from n goes from 0 to infinity of all that. So we have t to the n over n factorial a to the nth power like this. And then on the right-hand side, we have 1 over s minus a. And again, in terms of a series, it's equal to this, isn't it? Yes, it is. So we can just write that down, the series as n goes from 0 to infinity. And we have 1 over s to the n plus 1 times a to the nth power. Now, here is the thing you have to just believe me in this case. Well, Laplace is actually linear, meaning that the Laplace of a sum is the sum of the Laplace. And even though inside it's an infinite sum, but let me just tell you, it will still work in this case, right? Because this right here converges. So what we can do right here is that we can switch the order of the Laplace and also the summation. And if you want to see the detail, you can just change that to improper integral and work that out. But again, let's just do it right here. We have the sum as n goes from 0 to infinity. Let's put that down first. And then we have the Laplace transform of whatever we want inside. Now, here is the deal. Have a look right here. Inside here, what I want to do is, you see we have t to the nth power. I'm just going to have that inside of my Laplace transform. So we have a Laplace transform of t to the nth power like this, right? And then on the outside, we have the 1 over n factorial. Let me just put that down right here. And then at the end, we still have the a to the nth power like this. So have a look. This is a summation of all that. Again, technically, everything should be inside of the Laplace. But I took out 1 over n factorial and also to put that a to the nth power on the outside. And the reason I can do that is because in the Laplace world, only t matters. T is the variable. And the n is just like a constant, so just take that out. You can just take that out. So that's the idea. All right, and then on the right-hand side, we have this is equal to the sum as n goes from 0 to infinity of 1 over s to the nth plus 1. And here we have a to the nth power. And here is the punchline. Maybe you can see already, which is very nice. Have a look. The left-hand side and the right-hand side, they are both series. And you can just look at this part. This is a to the nth power. Likewise, this is also a to the nth power. So it's like infinite polynomial, right? Or infinite power series. Namely though, you see that this and that, they have to be the coefficients. And in order for the polynomials to equal, or the infinite series to be equal to each other, the coefficients have to equal to each other. So we can conclude that this and that must be the same. So with that said, you see here we actually just have 1 over n factorial, the Laplace transform of t to the nth power. This has to be the same as 1 over s to the n plus 1. So as you can see, in the end, all we have to do is just multiply the n factorial on both sides. So you can just see that if you were like, this is so nice. They cancel out nicely, and then in the end, you get the Laplace transform of t to the nth power that's equal to n factorial over s to the n plus 1's power. So here we have it. This is it. And technically, right here, as I said, n is going from 0 to 0, 1, 2, 3, and so on to infinity, and that's exactly what we use right here, so all that good stuff. So again, this is n factorial over s to the n plus 1. Very nice. Right? So that's it. All right. So you can see that this is actually really useful, and then we'll be using that for the coming up ones as well. Very cool. The next one is sine and cosine. Yes. Actually, questions 3 and question 4. We'll be doing two things in one. So this is like killing two birds with one stone. But we're actually not going to kill birds. We'll kill Laplace transforms. All right, so here we go. This is question number 3. I just want to make sure that I'm still recording. So right here, question 3, we want to have the Laplace transform of sine bt. And b is just a number, of course. So we need to know what this is. And of course, when we have sine, let's also talk about the cosine as well. So I'll put down number 4 right here. Number 4, Laplace transform of cosine of bt. And in fact, you can do this a few ways. First way is you can use integration by parts, and again will be similar things to the things that you have to do with t to the nth power if you use integration by parts, and you have to plug in the limits and all that stuff. In this video, well, I forgot, I'm just making one video. Here I will show you guys how you can use complex numbers to take care of both of them with just one computations. And another thing you can do is you can figure out sine of t and cosine of t, and later on use one of the properties I'll show you, and you can generalize it, sine of bt and cosine of bt. But anyway, here is how we are going to do it. Again, I'm going to write this down right here for you guys. We are going to use the fact that we did earlier, the Laplace transform of e to the at. This is being equal to 1 over what? Yes, s minus a. Yeah? All right, so this is what we are going to do. We are going to live dangerously sometimes, meaning that we will have to go to a complex world sometimes. So have a look with the a right here. Right? What we are going to do is I'm going to let a equal to, well, we have to have the complex number, so we have to introduce the I. And then over there, I'm using the b, so I will just have IB like this. So by using this, you will see that the next line we will have the following. So I will just put this down in black. Yeah. So this is what we have, and now we'll just use that. So here we have the Laplace transform. Excuse my little brace. It's really hard for me to do that, but anyway. E is E, and then the A is now IB, and then we still have the T. And then this is equal to 1 over S minus IB like this, right? So we can just, of course, do that. And now another thing that you have to remember is the Euler's formula. So let me also write it down right here for you guys. So this is the Euler's formula, which says when you have e to the I theta, this right here is nicely equal to cosine theta plus I sine theta. It's an amazing formula, right? And how we are going to use it is, well, the left-hand side is precisely cosine and sine already, yeah? And then the right-hand side is a rational expression we'll just have to fix that a little bit. Because remember, I don't like to be on the bottom, I like to be on the top, and then we can just work that out, and that's pretty much the idea. So here we go. This is how we are going to do it. The left-hand side, have a look. We have the theta being the bt right here, right? So the left-hand side is technically equal to the Laplace transform of sine, well, actually cosine first, of bt. So we put that down right here. And then we add I times sine of bt. So this is what we have on the left-hand side. And now, on the right-hand side, to fix that situation, when you don't like to be on the bottom, go ahead, multiply the top and bottom by its conjugate. So we get s plus ib, and then s plus ib, like this and like that. All right, on the bottom, let's do this in your head. When you multiply this out, you just get s times s, which is s squared, and then minus, and I times I is I squared, so it becomes -1, so it becomes a plus, and then we have b squared. So this is what we have on the bottom. And on the top, you see that we just have s plus ib, just like that, isn't it? Now, here is the cool part. Again, Laplace is linear, meaning that the Laplace of a sum is the sum of the Laplace. And when you have a constant multiple, you can also put that in the front of the Laplace. So have a look. I'm going to break this down as the Laplace transform of cosine of bt. And I'll close that, and that's added with, I will put the I to the front, and then we have the Laplace of sine of bt, like this, right? So I just broke, broke them apart, like this and that. And again, just really excuse my little brace right here. Here we go. All right, and on the right-hand side, we can do the same thing. We have the real part and also the imaginary part. The real part is just this, which is the following, s over s squared plus b squared, and then plus I times b over s squared plus b squared. And now we'll play the game. The game is called mix and match. Very fun. Because this and that, they are both the real part. So, of course, this has to be equal to that, isn't it? And then this is the imaginary part, so is that. So this has to be the same as that. And with that, we are done, because you will see that the Laplace of sine bt is nicely equal to this. We have the b on the top over s squared plus b squared. Again, we are done with that. And then for this, we will have that. S is on the top. S over s squared plus b squared, like this. There's no 5 in my video, right? So just s. This is now 5. Anyway, that's it. Very cool, huh? So you don't have to do the integration by parts like so many times. So this is so wonderful. So have a look. This is it. All right. Now we did 4 already. So this is going pretty well. And then I have some surprising integrals for you guys as well. So be sure you watch that as well. I say a lot of well. Well. Now, what's the next one? Ooh, remember the sinh and cosh, which is like the knockoff version of no. The sine cosine. Anyway, here we go. Number 5 and number 6. Well, here, let me just write that down. Number 5. We have the following: the Laplace transform of sinh t. Right? Sinh t, which is the hyperbolic sine function. Well, again, in this case, if you would like, you can go ahead and use the integration by parts with the definition of the Laplace transform, but we can do the following. Here we go. You have to remember the definition of the sinh function. Well, this is equal to the following. This is nicely equal to e to the positive input right here, which is t, and then minus e to the negative t all over 2, like that. And do we know how to handle the Laplace transform e to the some number t already? Yes, we do. So we can actually just break them apart, and let me show you how. First, we have the 1/2. Let's go ahead and put that all the way in the front. And then again, we can just do the following. Laplace of the first, which is the Laplace of e to the t, and then minus the Laplace of the second, And then we have the 1/2 all the way in the front already. So this is what we have. Yeah, I put on the BT, I'm sorry. I put on the BT. Sinh of BT, I'm sorry. So BT is actually our variable of our input, right? So I will have to change this to the BT, that's all. So easy fix. Here we have e to the BT, and then here we have e to the negative BT, and then this is e to the BT, and this is e to the negative BT. Okay, so just easy fix. Now we can continue. For this right here, of course, again, the 1/2 is just all the way in the front, like this. And then for this one, of course, we can just recall the formula, which is just 1 over S goes first minus BT right here. So you actually just put on B like this, and then minus 1 over, and we have S minus, this is negative BT, so we will actually have going to get a plus later on. So this is what we have. And now, of course, we can just combine the little fractions and all the stuff. So right here, we will just multiply the top and bottom by S plus B, and then S plus B. And I will just multiply this by S minus B, and then multiply the bottom by S minus B. So all that good stuff. Now we have 1/2 in the front. And then on the bottom, you just have S minus B times S plus B, which is S squared minus B, like this. And B squared, sorry. And on the top though, we have S plus B. So let me just put on S plus B minus S, and then minus becomes plus. So we have a plus B like this. And of course, just work that out. You can see that the S and S cancel, and on top, B and B is just go ahead and you have 2B. And then in the end, of course, you can cancel the 2 and the 2 right here. So this is very similar to the original sine function, yeah? You actually end up with B on the top as well. Over the bottom is S squared minus B squared like this. So that's it. However, do we need to put on any conditions? Well, have a look here. From here to here, remember, we will have to put on S is greater than what? S has to be greater than B. So I will actually have to say S has to be greater than B. Let me actually just write that down right here. S has to be greater than B, just like what we did earlier. And now this right here, you will just have to make sure that S has to be greater than this input, which is negative B. And depends on what B is. So you can just kind of include that and all that stuff, but I'm just going to leave that to you guys because I don't know if B is negative or positive and all that. But yeah, you can just say S is greater than B. That's actually pretty okay already. Anyway, this right here is B over S squared minus B squared, like this, right? And number 6, very similar, Laplace transform of cosh, but the input here is BT again. Actually, this is cosh, same input. Now, remember, the definition of cosh is the following. Cosh is nicely equal to e to the input, which is BT, and then plus e to the negative input, which is negative BT, all over 2, like this. And then again, we can just do what we did over there. So this is the same as 1/2 Laplace transform of e to the BT. And then we have to add the Laplace transform of e to the negative BT, like this and like that. And again, let's just go ahead and do this. This is 1/2 times, this is 1 over S minus the B right here. And in this case, we are adding 1 over S negative, and then this is negative B, just like that. And again, let me just show you guys this real quick. For the first one, we will just again multiply by S plus B, and then for this one, we multiply by S minus B, and then S minus B. And let's see, all the way in the front, we still have the 1/2. On the bottom, again, is going to be s squared minus b squared. On the top is s plus b. And then this is plus, and this is s, and then this is minus b. So it's like that. And in this case, the b and b cancel. S and s is 2s. So the 2 and then the 2 cancel. So in the end, we end up with an s on the top. So this is the s version. And again, it's very similar to the original cosine of bt. So this right here is s on the top, but you have s squared minus b squared on the bottom, like this, right? And again, you can tell me what the condition is. Just go ahead and write that down. That s should be greater than b, and yeah. Because it doesn't really matter in here because you square that anyway. So I'll just have to make sure s squared has to be greater than b squared. And yeah, just that's all. All right. So that's pretty much it. And continue. We're doing pretty well for this one. Better than the differential equation. Huh? So we have the next one, which is the unit step function, like this. Right? Okay, so let me erase all this. So again, as I said, we'll be using definitions whenever we have to do proofs. But sometimes if we can see the connection between the things we have done already, you don't have to use the definition. All right, number 7. I'll put this down right here for you guys. 7. Laplace transform. And here we have the unit step function, so I'll just put this down like that. This is the best I can write. T minus some number a, like this. Yeah. All right, and right here I will have to remind you guys what the unit step function is. This right here, it's actually a piecewise function. So I will actually draw it for you guys first. The idea of the unit step function is that if you have the following, yeah. Let me see. Let me just do like this. Look at what the a is first. So let's say here is my a. And anything before a, when you are doing t minus a, anything before a is 0. So you have this. And then you put on the open circle. And then after a at a, you actually jump to 1, right? And then it's an open circle as well, like this, right? So the idea of the unit step function is that if the input is positive, then you get 1. If the input is negative, you get 0. And if the input is 0, some books define it to be 0, some books define it to be undefined. So I will use the open circle in this case. So I will write this down right here for you guys. U of t minus a is equal to either 0. Again, if the input, so I will write down t minus a is less than 0, right? And it's equal to 1 if the input, namely t minus a, is greater than 0. And the reason I want to do this is because I would like to tell you, if you reverse the t minus a with a minus t, you just reverse the picture. But that's happening later on, so no. So keep that in mind. If the inside is positive, then you get 1. If the inside is negative, you get 0. If the inside is 0, some books define it to be nothing. Some books define it to be 0 or 1. Depends. Doesn't really matter because we are doing integrals. So 1 point is not going to change anything. Anyway, how can we do this? Yes, definition of the Laplace transform. So let's write it down. This is the integral going from 0 to infinity, e to the negative st times u of t minus a, like so. And then we have the dt. How can we do this though? Well, have a look. This is what's going to happen when you multiply a function with a unit step function. So let me graph e to the negative st for you guys, which is just an exponential decay function like this, assuming s is positive. So this is e to the negative st, right? And originally, this integral, we had to go from 0 all the way to infinity, yeah? But now, after we multiply by the unit step function, so I will write this down. If you have e to the negative st, unit step function of t minus a, what's going to happen is that, well, figure out where a is, let's say it's right there. Anything before a, this is 0, 0 times this, that will make everything 0, right? So actually you just get 0 right here, and then you have an open circle. At a, there's a jump to 1, and 1 times this is just that, so you will just jump to here, and then you have this. Okay, so instead of integrating the whole thing, have a look. You actually do not have any area from 0 to a at all. All we have to integrate is just from a to infinity, just this part. And again, at the endpoint right here, it's just a point, so if you're talking about the integral, it doesn't matter. All right, so here we go. We just have to integrate from a to infinity. And again, this right here changed the 0 to a, and from a to infinity, this portion is just the same as the original. So I can just write down e to the negative st, like so, and then we have dt like that. And then again, right here, we can just go ahead and integrate out of this. So integrating this is just e to the negative st, and then we divide it by this, right, which is just going to be 1 over negative s. And then we plug in, going from a to infinity. Well, when you put infinity here, we have 1 over negative s, e to the negative s, and we have the infinity right here. And that's the first part, and then I have to minus. The second part is 1 over negative s, e to the negative s, and then you have the a like right here. All right, is this going to be 0? Depends on what s is. This is negative already, this is positive infinity. S has to be positive so that we can actually get negative infinity out of this, right? So with that being said, s has to be greater than 0. So with that condition though, we can actually say the first part has to be 0. And again, we need to have that condition. Anything that I write this down right here is that we need to have that in order to make this work. And work out the rest, negative becomes positive, and then we just have that. That's pretty much it. So in the end, we have the plus 1 over s e to the negative sa. So finally, we'll just write this down as e to the negative sa. And some people like to write it as e to the negative as. It depends on how you want to write it, but this is okay. And then over s. Yeah? And again, we have the condition, so let's write that down. S has to be greater than 0 in order for that to work. Just like that. Right? So this right here is a unit step function. And now let me introduce you guys something that's very similar to the unit step function, namely the window function. So it's the pi sub abt function. I should be able to do that right here, so I will do that right here. Number 8. So here we have the Laplace transform, and inside is the capital pi a comma b. This is not the original pi function, it's just I think it's called the window function or that. Oh, by the way, this is also called the Heaviside function, but it's not because this side's heavier, that's why it's 0. Heaviside is just a name of the person, right? Anyway, I thought it was something funny, but anyway. So we have pi ab, and the input is just usually with a t, like this. Right? So that's what we have. And again, I will have to tell you guys what pi ab is. Well, pi ab is actually not so bad at all. Pi abt, this right here, again, as I said, it's very similar to that. Perhaps I'll show you guys a picture first. Well, very similar. You have to tell me two numbers, a and b. Suppose b is bigger than a, right? So let's say we have a here and b here. The idea of this right here is that anything outside of a and b is going to be 0, and anything between of A and B is equal to 1. That's pretty much it. So you can just grab it right here, open, open, like this. Anything outside is 0, and then anything between is 1. And again, we do not worry about the endpoints, right? So just have that. And then here is the property of the pi AB of t. So you can write it down like this. 0, I should write down 1 first. 1 if the input is in between of A and B. And again, do not worry about the endpoints. 0 otherwise. Okay? So hopefully you guys, this is the problem. 0 if otherwise. If otherwise. No, that doesn't make sense. If otherwise, all right? So just, I'm sorry about the words otherwise, meaning that there. All right, so that's pretty much it. However, there's a really nice connection between the unit step function and the pi AB. I will also tell you the pi AB is actually just nicely equal to the unit step function of t minus a, which is this part, and then you minus, right? You minus ut minus b, like this, right? Oh my God, I'm so sorry. There. All right, so just like that. All right, with that being said, in order to do the Laplace of this, we can actually just use this right here, which is very nice. So we actually just have to do the Laplace transform. Again, pi AB is just going to be the unit step function of t minus a, and then minus the unit step function of t minus b, like this, which is very nice. Because now we can just do a Laplace transform of the first one, minus Laplace transform of the second one. Laplace transform of the first one is what? It's kind of hard. Well, no, not really. It's over there. So we actually just get e to the negative sa over s, right? That's pretty much it. That's all we have to do. And s has to be greater than 0, just like that. And then in between is a minus, so just go ahead and put down minus, and then we have this. So all we have to do is change the a to b. So we have e to the negative sb over s. In the end, of course, let's write things down together. E to the negative sa minus e to the negative sb all over s. S has to be greater than 0. And with that, we are done. Just like that. Right, so this is the window function, I believe. That's the name of that. So it's the pi AB business. All right, next one is going to be pretty crazy. It's still kind of like a piecewise, but it's not as normal looking as the one that we just did. So have a look, all right? Have a look. And let me know if you guys are taking differential equations. If you are, man, I missed that class. I'm not teaching differential equation this semester though. I haven't taught it in 3 years, but you know, I just feel like doing some Laplace transform. So why not? All right. So this is the number 9, and this is the Laplace transform of the Dirac Delta function. So you just put down the delta. This is the delta, and then t minus a, like this. Right? So again, I will have to explain to you guys what the delta function is. Well, draw a picture. Tell me where a is. Anything besides a is 0. So you have all this. Open circle. So what happened at a? The function goes up to infinity, all the way to infinity, all the way to infinity. You cannot even see it. Seriously, you cannot even see it. So if I, let me just, I don't know, just cannot see it. So it doesn't really make sense for me to graph that. You just have to grasp it from the definition that I'm going to write it down, right? So here is the deal. I will just have to write it down for you guys. The delta t minus a, again, I will write down the name later, but this is 0 if t is not equal to a, and this is equal to infinity if t is equal to a. So again, the picture is everything is 0 except for a, it goes up to infinity, right? So there's no way for me to give you guys a legitimate graph for that. And again, this is called the, well, I should write down the name because this is direct. What's a t? Direct. I think it's a t, delta function, right? Maybe without t, I don't remember. What's a t? I didn't write it down. I don't know. But anyway, I'm sorry. Let me actually just not write down the name. Yeah, there we go. Much better. All right, so this right here is what we have. Now, this is how the Laplace transform is going to look. This right here, we are going to use the definition and see what happens. So, integral from 0 to infinity. Again, we have e to the negative as t. And then we are going to multiply this with delta of t minus a like that, and then dt like this. How in the world can we make that happen though? Well, I have to tell you guys a few more things about the delta function right here, right? So one property that you have to know is the following, right? If you integrate from negative infinity to positive infinity, because the domain is the all real number, so you go from negative infinity to positive infinity. It doesn't really matter actually. And if you integrate delta of t minus a right here, let me just ask you guys this question first. What do you think what the answer is? And again, you can just really imagine that you have the graph, but it's not ideal to have a graph. A is right here. For delta is everything 0, but when you have a, it's going to be infinity. And remember, when you have integral, you're trying to find the area. The area right here is 0. The area right here is 0. What's the area? Like, let's say this right here is the infinity. This is like the infinity, so up here, right? We have 1 point. What's the area from here to here? Is there any width? No, the width is 0. But what's the height? The height is infinity. What's 0 times infinity? Technically, it's indeterminate, right? However, by definition, the best part about this right here is that this right here is defined to be 1. This is the property of when you integrate the delta function, all right? So you have to just kind of take my word for that, if you would like, right? So that's the idea. That's the idea number 1, right? And in fact, you also have idea number 2 right here. If you have the following, let me erase my picture and let me erase the infinity here. Idea number 2, if you have the integral from negative infinity to positive infinity, if you have a function, let's say f of t times delta of t minus a, like this. Well, again, let's just think about as a picture. Here's a, anything but a is 0, like this. So this right here is going to give you infinity when t is equal to a. But this time, we have infinity times f of t. F of t at a is just f of a, right? So of course, when we have f of t at a is equal to f of a, that's clear, right? That's the value of the function at a, of course. But you have f of a times infinity. So earlier, the infinity was right here, isn't it? And suppose you have f of a times the infinity. So of course, it's like another multiple. You done multiple, just multiply by 1. That's all. So whenever you have this, all you have to do is put a into the function. So you actually just get f of a. That's it. Again, it's just like the infinity times whatever that number is. That's it. And then you integrate that, so of course, just take that number to be the answer. So this is like the craziest part. Yeah. Well, with this being said, in fact, this right here is super easy because all we have to do is notice this right here is the delta function. And again, this right here, even though it's going from 0 to infinity, it's the same as going from negative infinity to positive infinity because everything is 0 only when t is at a, right? So earlier I had negative infinity to infinity. That's why I said doesn't matter. All you have to do is the following. Put a into the variable t right here, and that's it. So finally, we just have e to the negative s a. That's it. Yeah, seriously, that's it. As crazy as it looks like, and you just really have to take the definition as how it is, because 0 times infinity from your Calc 1, Calc 2 classes, you should know that it's indeterminate, meaning you have to do more work in order to figure out the answer, but we'll take that to be 1 in this case. All right, pretty cool, huh? Okay, that's number 9. Okay, now this is somewhat crazier, so we'll be doing number 10, and this time I will be doing 2 of them for number 10. So here is number 10. Laplace transform of f of t minus a, sorry, wrong color. Laplace transform of f of t minus a. And you see, usually it's just f of t, but when you have f of t minus a, that's how you shift the function, either left or right, depends on what a is. And then, not only this though, we also have the unit step function after that. So this is the first one for number 10. Meanwhile, you might be thinking, what if we just have f of t, right? So I will also have to show you what's the Laplace transform of f of t only, and multiply by u of t minus a, like this. So it's some like the unit step function business again. All right, let's figure this out first. To do so, let's go ahead and use our definition. So integral from 0 to infinity, e to the negative st, all that, which is f of t minus a, times the unit step function of t minus a, and then we have the dt, of course. Let's see how we can do this though. Well, again, whenever you multiply this, you just have to observe what's happening right here, right? So I will draw the picture one more time for you guys, just in case if you skipped what we talked about earlier. So this right here, we are trying to find the area from 0 to infinity under this function. Let me grab this right here first, and I will do that with blue. So I will put this down right here, yeah. E to the negative st times that, let's say the function looks like this. I don't know though. E to the negative st f of t minus a, right? So let's say the function looks like that. And again, you have to tell me what a is. Let's say it's right there. So this is how the function looks like, just this. Now I will graph e to the negative st f of t minus a times u of t minus a. So here is going to be the change after we multiply by that. And the only change is that, well, anything before a, it's going to be 0. So we have this right here, like that. And then you jump to 1. And 1 times this is, of course, just that. So anything after a is just the original blue curve, like that. So it's similar to what we did earlier. And if you want to find the area from 0 to infinity of this, you can just find the area from a to infinity of the blue function. So that's pretty much the idea. So here is going to be the integral from a to infinity. So I will actually put this down in blue. Why not? A to infinity. And then the inside is just going to be the following. E to the negative st f of t minus a. That's it. dt that guy. Yeah. Now, how can we handle this though? We haven't done some legitimate integration for a while, huh? Especially for this video. Let's do some fundamentals, namely u substitution. So let's go ahead and do u substitute. But we used the u already right here, so let me use v, right? So I will say v is equal to the input, which is t minus a, and then v is equal to dt. So that's pretty good. Now take this integral to the v world. Well, keep in mind, this right here is t goes from a to infinity. Now take this integral to the v world. V will go to where? Start here where? You put a right here, a minus a, we get 0. And then you put infinity right here. Infinity minus a finite number is still infinity. So v goes from 0 to infinity. And here we have e, and then we have negative s. T is what though? Well, we know v is equal to t minus a. So of course, that means t is equal to v plus a, like that. So I will just put that down. This is v plus a, parentheses that guy, and then we have f of v, and then dv and dt are the same, so I can just put that down right here. So that's pretty nice. And now we'll finish everything in the v world. V is just a dummy variable, and we just have to figure that out. Well, right here, of course, we can just work that out a little bit. This is e to the power of negative sv minus sa, yeah? Now, have a look. E to this power is the same as e to this power times e to that power. E to the negative sa, well, that's just a constant in the v world, so we can just put that to the outside. So this is going to be the following. Let's write down e to the negative sa first, right? And then for the inside here, have a look. This is going to be the integral going from 0 to infinity, and we have e to the negative sv, and then here we have this, namely f of v dv, like this. What's this? Well, here is something really nice. In the front, we still have the e to the negative sa. But this right here is what? This is just nicely equal to our definition of the Laplace transform of f of t, isn't it? Even though I'm using v, and v right here, but v is just a dummy variable. As long as you have this, and that being the same, well, it still goes from 0 to infinity. This is still going to be the Laplace transform of our function, which is f of t, like that, right? So this right here is it. So this right here is just translation formula. So all you have to do is, when you have e to the negative sa, when you have the function multiplied by the unit step function, if they have the same input, all you have to do is, in the s world, be sure you multiply by e to the negative sa, and then you do the Laplace transform of the original function. And that's pretty much it. And now, I just recall that I haven't write down this for you guys. Usually, we can write this down, yeah? It's e to the negative sa. And this right here, we can put it as capital F of s, like this, right? So this and that, just a standard notation. The output of the Laplace transform of f of d t is just f of s, right? So you can just keep that in mind. I'm going to write this down right here, though, I think, and I hope it's more clear this way. So I will put this down right here, e to the negative sa, and Laplace transform of f of t, like that. You can just write it down better for you guys. F of t. All right, so that's the first one. I will show you guys 2 examples, don't worry. But we're not done yet for number 10. Because what if the input right here, they don't match? Ah, no good. Don't worry, I got you. So have a look here. Well, if the input don't match, you can do the following. Make them match first. So I'm just going to start by saying let, so this right here is the second question, yeah, kind of, it's like 10.5. Let g of t minus a be this, right? And why do you want to do that? Because now I can legitimately put this down right here, isn't it? So here we go. I will just write this down right here for you guys. this is going to be the Laplace transform. F of t is going, let me just write it down again. F of t, and we have the unit step function of t minus a. This now, I can just put it down as g of t minus a. So we can say this is the Laplace transform of, can we still see? Yes. G of t minus a and multiplied it by u of t minus a, like this, right? And do we know how to handle this? Yes, we do. Just that. But instead of using f, we will have to use g, right? Because I'm saying g t minus a, u t minus a. So this right here is nicely equal to, you just do the formula, namely e to the negative s a Laplace transform of g of t. Like this. Yeah. So that's pretty much it. But the problem is that, man, I'm trying to show you guys the function with f, and now I have a formula with g. So what the heck is g, right? Don't worry, I got you. Again, if you look at this, g of t minus a, which we set it to be f of t, well, all we have to do is kind of shift it back, because I just have to figure out what's g of t in terms of f. That's all. And to do so, all we have to do is change the t to t plus a. You see, t plus a minus a is just t. Likewise, we just have to do the same right here, t plus a. So you will see that g of plugging, you actually just get t, and plugging, you just get f of t plus a. So in another word, this is the same as that. Well, finally, you can just write this down right here as e to the negative s a times the Laplace transform of this guy, which is our f of t plus a. Just like this, right? Well, here is the moral behind the story. If this right here is just f of t, which is not with the same input as that, all we have to do is the following. You still multiply by e to the negative s a. Whenever you have the unit step function, just go ahead and do that, right? Just go ahead and do that. But if they don't have the same input, all you have to do is do the Laplace transform of f. And you just have to compromise it. This is minus a. You go ahead and do f of t plus a. So this right here is it. Can we see? Yes. All right. So that's the idea, and that's exactly what I just showed you right here. All right. So I did 2 in 1, and now I will show you guys 2 examples for the next question. So let's go ahead and do the following. Yeah, and to be very honest with you guys, I do miss my students. I haven't seen them for a while. And hopefully everybody's doing well, and hopefully my students, you guys are watching, and you guys are doing well too. All right, so now number 11. 11 deserves a happy face, like that. All right, so we have 2 examples right here for you guys. First one, let's see the Laplace transform of t minus 2 squared times, I forgot the input should be in red. All right, number 11, Laplace transform of t minus 2 squared, t minus 2 squared times the unit step function of t minus 2. So in this case, the a is clearly equal to 2, right? Versus the second one, the Laplace transform of just t squared times the unit step function of t minus 2. Right? Which one is easier? This one, slightly easier, not so bad though, because again, just the computational is slightly easier. It's not too bad. All right, all we have to do is the following. They do have the same input, and the a right here is 2. So all we have to do is, first, you go ahead and multiply by e to the negative s, and the a is 2. So 2s, like this, yeah? And it's really evil if you ask Laplace transform questions and you have like t minus 5. because you have to put 5 right here, and it becomes e to the negative s and then 5. So I usually try to avoid not use 5. Nobody can understand what this is. So this is s, that's 2, yeah? That's pretty clear. Anyway, you do this part first, and then the next part is you go ahead and do the usual Laplace of f of t, which you focus on this part. Just ignore the input, just look at the input as t only. So you have to do t squared, like that. All right? Now, how do you do that? Well, we did that earlier for question number 2 already, right? So you have to remember these kind of things. I will write this down right here for you guys. Recall that for question number 2, Laplace transform t to the nth power. This is equal to n factorial over s to the n plus 1. So all we have to do is the following. Here we have e to the negative 2s. This is not 25, this is 2s, negative 2s. And then for this, n is 2. 2 factorial is 2, so we just multiply by 2. Over 2 plus 1 is 3, so you have s to the third power, like that. Right? That's pretty much it. So in the end, of course, you can write this down in a nicer way. Maybe you can write it as 2e to the negative 2s over s to the third power, like that. So this right here is it. So again, this is s, right? And again, this is meant to be 2 factorial, but 2 factorial is 2 times 1, which is the same as 2. So no worry about that. Now, have a look here. How to do it? The inputs are not the same anymore, but we can use this right here, right? So what we have to do is, first, notice that our a is again 2. So go ahead and do this, which is e to the negative s times 2. Then what we are going to do is multiply by the Laplace transform. The function here is t squared, but this case you have to do t plus a of the function, right, inside of the function. So we will have to put t plus 2. So I'll just write down t plus 2 inside of the function, and then we have to work this out. How can we work out the Laplace transform of t plus 2 squared though? Don't worry, just do some algebra. So here we go. This is just e to the negative 2s. Multiply this out the usual way. So we actually get the Laplace transform. This is going to be t squared plus 2 of this and that, which is going to be 4t, and then lastly 2 squared, which is plus 4, like this. Yeah? So just like this. And then all in all, we can just do this, this, and that by using that. This case is when when n is equal to 0, right? When t to the 0's power. So, right. So here is e to the negative 2s. See, I make the mistake again. This is e to the negative 2s. Okay, t squared, which is the same as that. I'll put down the parentheses for the result of the Laplace transform. Here we have 2 factorial, which is just 2, over s to the third power. Double check. Good. Well, it's right there, so yeah, obviously. Next, 4 is just 4. And then the Laplace transform of t is going to be 1 factorial over t squared, right? N is 1. So on the top is 4 times 1, which is 4 over s squared, like this. And lastly, this is going to be plus 4. And again, this is t to the 0's power. And 0 factorial is equal to 1. And then put the 0 here, you have s to the first power, namely 4 over s, like this. And usually, nobody will make you combine fractions for Laplace transforms. So I think this is totally okay, right? So just leave it like that. If you combine the fractions, I don't think you can impress anyone anyway, so just leave it like that. Anyway, number 11, that's it. Okay? Okay. All right, so now we will be doing some more proofs, that kind of things, right? So continue, number 12. Here is the Laplace transform of f a t. F of a t. Please do not call this to be fat, and it's not nice. Just say f of a t, yeah? All right, so here is the deal. I'm going to, again, I should write this down right here. For now, just make a note that when we have the Laplace transform of our function f of t, this right here we can write it as capital F of s. Right? That's what we mentioned earlier. And for number 12, if we have the Laplace transform, but the inside is not just f of t, but rather is the Laplace transform of f of a t, like this. First thing first. Yes, the input is at, it's just a multiplied by with t. But right here, it's not going to be the same as f of as. It's not like this. This is not true in general, right? Unless a is equal to 1, but that's redundant. So we actually have to do this carefully. And now, here is how we are going to do it carefully. Use definitions, of course. So integrate from 0 to infinity e to the negative st of f of at. So I'm sorry again, I forgot to make the inside red. F of at. So I will write it down, f of at, like this. And then we have the dt right here, right? So again, let me just cross this out. No. How can we make this happen though? Again, u substitution. So here, I think the best choice is to have the at to be our u. And we haven't used u in this case, so we'll use u. Yeah? So let u equal to at. And of course, a has to be a legitimate number and all that stuff. And oh, I forgot. Let me just prove the case that when a is greater than 0. Right? Let me just say the case when a is greater than 0. And yeah, it's cleaner this way. Yeah. Anyway, u is equal to at. Sometimes a is not greater than 0. You can use some properties, and in fact, it's still true anyway. By the way, du is equal to the derivative of this, which is a dt. dt is equal to du over a, right? And again, we have the condition a is greater than 0. And this is why we have to have that condition to make our proof easier. All right, for our integral in the t world, it goes from 0 to infinity. So that means t goes from 0 to infinity. Yep. Now, let's go ahead and take this integral to the u world. Well, u is the same as at. A is positive. And when t is 0, we get u being 0. And when t is infinity, you put it here. A times infinity. A is positive. You get infinity. Right? So that's pretty much it. And then you just continue. E, and then you have negative st, and the t, we have to solve that. So let's go ahead and do that. Just divide both sides by a, we get t equals a u minus u over a. U over a. United Airlines or something like that. Anyway, so s is still s, but t is u over a. And then here we have f, and the input is the u now. And then dt is equal to this, so I will write this down right here for you guys. This right here is my u, and then the dt is this, so you have the du over a, like that. Right? So now, let's just go ahead and do all the rest. So here's the usual business. We have the 1 over a, we can put that all the way in the front, and we'll finish everything in the u world. So we have 1 over a, integral 0 to infinity. They are in terms of u, right? It's very nice. Now, here is the deal. I'm going to rewrite this as follows. E is E, negative, and have a look. Let me write this down as S over A, and then times U right here. Right? Times U on the side, like that. Right? And then, this right here, I'll write it as F of U. And then, on the outside here, of course, we still have that du. So this is what we have. Now, have a look. 1 over a is all the way in the front, so that's nice. What's this though? Well, u, and u match, and this is integral going from 0 to infinity. So this is almost like our Laplace transform. And you have to remember this right here, the definition was integral going from 0 to infinity, and we have e to the negative whatever that we have here, right? S t, and then f of t dt, right? You see f of s and that match, and then the t match, and we have the negative and also the infinity 0 on the stop. Here, this right here is our new input in the S world. So all we have to do is put that down into capital F. So we have capital F of S over A, just like that. Therefore, the Laplace transform of little f of at is equal to 1 over A capital F of S over A, like this, right? And again, I only proved the case for A is greater than 0. You can go ahead and try it if A is less than 0. Just some bizarre part like with the limits of the integration, you have to fix that. It'll still work. And sometimes if you don't want to go through all this, you can just use the property of some function to make the negative go away if necessary. But anyway, this right here is it for number 12. All right, so this is how you change that. Oh, by the way, let me just do a quick example for you guys how you can make this work. This is actually a little bonus. I didn't prepare that, but I want to show you guys how cool this is. So, real quick example. Suppose you know this. The integral of sine t is equal to, which is with the 1 on top, 1 over t, s squared plus 1 squared. So just like this. S is the sign is with the b on top, and this is b is 1. Now, if you know this, this is what we know. And if you want the Laplace transform of S of dt, well, this right here is precisely our f of s. And have a look. Here is the s, here is the s. Yeah? Here, we can use that formula. This right here is a number multiple. Earlier I used AT, but here I'm using BT because I can match with the formula that we got earlier. But anyway, what we can do is just go ahead and do 1 over whatever this number is. Yeah? And then you put down S over B in here. So you just go ahead and do F of S over B. So we get 1 over B. F of S over B, you just put S over B right here. So we multiply by 1 over parentheses S over B, and you square that guy, and you plus 1 after that. And then you will see, right here, we can just get the common denominator, which is going to be B squared. So go ahead and do that, and multiply on the top. So you get actually 1 over B times B squared over this and that is just S squared. This and that is B squared. And of course, this and that cancel. Doesn't this look familiar? Yes, it does. It's just b over s squared plus b squared. So that's how you can use this formula to generalize. Sometimes don't worry about the constant multiple. Just put on 1. And after that, you can generalize it by doing that. Whew, okay, so that's it. All right, so number 13. And again, the capital F of S is just the result of the Laplace transform of the little f of t. Number 13, we're going to multiply by something else. So number 13. Laplace transform of e to the at, e to the at. So it's eat. This is eat, f of t. So you eat, that's again, color, right? E to the at, f of t. So here is the deal. You'll notice that when you have a Laplace transform of a product of two functions, in fact, there's not a good formula in general. Only if you know a function, it's like a special one, such as this one. If you have e to the at times f of t, this right here is actually rather special, and I'll show you guys how we can actually, come up with a nice formula for this, right? So here we go. Use definition. So here we have the integral going from 0 to infinity, e to the negative st, yes? And then you just put this down right here, e to the at times f of t, and then we have the dt after that, of course. Now, just do the integral pretty much. This and that, we can put them together, so we get integral from 0 to infinity, e to the, and let me just write it as a minus s. A minus s. And then we have, actually no. No. Well, technically this is negative s plus a, and then times t, yeah? If you factor out the t, and then you have f of t. Like this, all right? Good. Now, this is what we are going to do. Right here, I'm going to factor out a negative, and I'll do this in this order, right? So, I have the integral going from 0 to infinity, e. I will factor out a negative, and then input will be the following. I'll put this down in blue so it stands out a little bit better. Input will be s, and then minus a, and again, just work out the algebra, and then you have the t after that, and this is f of t dt. Do we need to use any u substitution? The answer to that is no, we don't have to. Because again, t, and t match, and this is a negative, and then you have 0 to infinity already. So just to remind you guys one more time, if you have the integral going from 0 to infinity of e to the negative s t f of little t dt, this right here is nicely equal to f of s. Yeah, this match. And now you have this. So what's that? That's our new input in the S world. That's it. So all you have to do right here is just write down capital F of S minus A like this. Very, very, very nice. So this right here is how you can translate in the S world. Earlier, when we translate, it has to be in the T world and use the unit step function. And if you want to make any shifts, you will just have to multiply the f of t with e to the at, right? So that's the idea. And now, of course, I'll show you guys an example. And I'll show you guys two examples, right? So let's do number 14. So the first one, I have this for you guys. Yeah? And then, in fact, I will just give you guys another one because I think I would give you guys two examples right here. First one, the Laplace transform t to the third power e to the 2t. I forgot to put it inside to be read. All right, number 13. T to the third power e to the 2t, like this. Right? In fact, you can do this with two ways. Depends on which one you take to be the original function f of t. Well, I'm going to do it with that way. So that means I will take this to be the e to the at, of course, and I'll take this to be the f of t. Yeah. So this is how we are going to do it. First of all, if you would like, you can put this into that form. It's not necessary, but I'll do it for you guys anyway. This is the Laplace transform e to the 2t, and then we have t to the third power. Right? Just like this. Then what we are going to do is we have to figure out what's the Laplace transform of t to the third power first. So I will just write this down right here for you guys. Laplace transform of t to the third power. This right here is equal to what? You do 3 factorial. So let's put down some color. This right here is 3. So you do down 3 factorial over s raised to the 3 plus 1 power. And what's 3 factorial? 3 times 2 times 1. That's going to be 6. So this is nicely 6 over s to the 4th power, isn't it? And in this case, this is our s right here. And pay attention, this right here is precisely our f of s. Right? So, what's the answer for this? Well, this right here is just going to be f of s minus 2. All we have to do is, instead of the s right here, you just have to substitute s minus 2 because the a right here is 2. And all you have to do is 6 on the top over s minus 2 in here, and then you raise that to the 4th power. So here we have the s minus 2 raised to the 4th power, and you are done. Again, this right here is precisely our f of s minus 2. Right here, this right here we have the 2, where f of s is equal to this, right? And then we know f of s is equal to that. So that's all we have to do. Very, very nice, right? So again, another number 14 as a little bonus, because I don't think I'm doing enough for the marathon, so number 14 again. So put a little star next to it maybe. Let's do another one. How about let's do a more bizarre one, Laplace transform, and let's do this. I would like to do e to the 3t, and then let's do a cosine one. So let's say cosine of t, like this. Well, in this case, again, we do the same thing. First, we have to figure out what's the Laplace transform of the cosine t. Actually, let's do cosine of 2t, why not? Slightly more numbers, more better. All right, so let's go and figure out what's the Laplace transform of this part, which is Laplace transform of cosine of 2t. And remember, cosine is the one that has the s on the top. So this is equal to s on the top over, and you have s squared minus b, which is 2, right? So you have 2 squared, like this. So that's pretty much it. 2 squared is 4, but I'm not going to write it down because this is not the final answer. Anyway, here is the s. So you know this right here is capital F of s. Yeah? And right here, you notice we are multiplying this with e to the 3t. So what should the answer be? Well, we just have to do s minus 3 in the capital F. That's all. So we just have to make sure we end up with capital F of s minus 3. So now, here you have s, here you have s. So go ahead and just have s minus 3 here over, put the s minus 3 here. Oops, wrong color. And then you square that. And then here you have the minus, sorry, cosines with plus. Cosines with plus, right? Cosines with plus. So you have this, and then in the end, you just add 2 squared, which is 4, like this. And then you are done. Right? So just like that. So this is not so bad, right? What if you have to go backwards? Well, maybe in the future, not today. Today is just Laplace. Maybe in the future, next time or so, I don't know if I can come with like 24 Laplace transforms for the inverse. I'm not sure. But anyway, this right here is it. Right? Maybe you guys can do it, or make that into a contest if you guys would like. Do like a inverse Laplace transform or something like that. If you're interested, let me know, and let me see what you guys would like to do and all that stuff, and I'll try to work things out with you guys. Oh yeah, next one is number 15. I was looking at what number should I be doing. Number 15. Here we have Laplace transform. And again, earlier I said a function times another function. Usually you don't have a general formula. But today, if you have a function that's the f of t, so that's a general case. But if you have this multiplied with just t to the 1st power, this actually gives you a pretty nice result, right? This actually gives you a pretty nice result. So let me see how we can actually make this happen. Of course, this right here is calling out, hey, we should use the definition. It's the integral going from 0 to infinity, and it's e to the negative s t, and you multiply with t f of t dt, all the stuff inside, right? Okay, but in this case, I don't think we can integrate this nicely, though. I don't know. So we have to do this from a different point of view, right? Let me just write this down right here for you guys. So let's see. This is what we know. Again, if you just have f of t inside, that's capital F of s. So let me put this down like this. We know that, let me write it down. Let me see. Let me write down, which one should I write down first? I want to write down f first, or should I write down Laplace first? Don't, just give me 1 sec. Just being picky, right? It's not like I don't know how to do it, it's just being picky. Hold on 1 sec. Oh yeah, let me just write down capital F first. So it doesn't really matter that much. We know that capital F of s, this right here is just a definition of the Laplace transform, meaning the integral going from 0 to infinity. And we will write this down better. Again, just being picky, I'm sorry, okay? All right, this is just the definition of Laplace transform, integral going from 0 to infinity, and we have e to the negative st, and we have little f of t, like this, right? So that's pretty good. Now let's make a comparison, this and that. This right here has an extra t. That's all. That's the only thing that's happening, right? I really want to just multiply the t inside with the integral, but we have to do that really carefully because we are in the t world in the integral, right? I have this t right here, and this is negative s. Imagine if I can differentiate this with respect to s, if I treat this as the variable, differentiating e to the negative st, where s is the variable, so we just have to do the chain rule, and we get negative t in the front. That's very nice. That's how we can squeeze out a t inside of the integral, right? So that's actually how we are going to do it. We are just going to look at this equation, and you see the left-hand side is a function in terms of x. So we are just going to differentiate this with respect to s, like this, right? So on the left-hand side, of course, this is just going to be the derivative with respect to s of our f of s, like this. So that's just going to be some calc 1 derivative whatsoever. But on the right-hand side, this is how we are going to do the derivative of an integral. You have to use what we call the Leibniz rule, and sometimes that's also called the Feynman's technique of integration. But anyway, if you do the derivative of this, you will just have to do the partial derivative of the inside first. That's okay. That's Leibniz rule. So let me write this down right here for you guys. We will first write down the integral from 0 to infinity. Instead of putting this on the outside, we are going to put this inside of the integral, and we will do the partial with respect to s. And the reason we change this to the partial notation, it's because the inside here, technically, we have two variables. But anyway, do the partial of this expression with respect to s. So I will write this down in red. We get e to the negative st, and then we have f of t. Then we want to focus on that, and then on the outside here, we still have the dt. And now let's focus on this part. So do this first. That means we can write down the integral from 0 to infinity, and then we still have the dt on the very outside. Now, here, we are taking the derivative of this expression in terms of the s, right, in the s world. So s is the constant, t is just the variable. S is the variable, t is just a constant. There we go. I'm sorry. All right, so I can just write down the constant multiple first, which is the f of t, no big deal. And then take the derivative of e to the negative st. Well, the derivative of this always repeat first, so we have e to the negative st. Then use the chain rule, as I mentioned earlier, multiply by the derivative of this. Derivative of negative st in the s world is negative t. So you just multiply by negative t right here. And that's so wonderful, isn't it? Because this matches with that. Very nice. Except for the negative sign. Well, what can we do with a negative sign? This is just a negative 1. We can kick that to the other side, right? So have a look. This is telling us the integral from 0 to infinity of positive t. And I will actually just write down everything like this. E to the negative st. Put a t right here. T f of t. And dt. This right here, again, we can kick the negative to the other side. So you just have to multiply the negative with the derivative in the S world of the capital of f of s, like this. So that's pretty much it. All you have to do is look at what f of s is, look at that first, and then go ahead, differentiate that with respect to s. Right? Sorry, let me just write down better for you guys. Look at what f of s is first, and then differentiate this with respect to s. But not done yet, because you still have to multiply by a negative. So that's it, just like that. Very nice. Now I will demonstrate an example for you guys. That's number 16. I'll just put it down right here. Should work okay. Number 16 is equal to the following: Laplace transform of t times sine of bt, like this. Well, if you're hardcore enough, you can just run through the Laplace definition again, but we'll just use the result. Now, here is the deal. You see, we multiply this with t to the first power. So I just have to figure out what's the Laplace transform of the sine of bt. So I will just rewrite. We know f of s, which is the Laplace transform of sine of bt. This right here is equal to b over s squared plus b squared. I am not making a mistake like earlier, so this is good. So this is our f of s. Well, this right here is equal to the following. We just have to go ahead and do the negative and differentiate this with respect to s of the function, which is f of s, which is just this. I'll just put this down, f of s. Yeah, and of course, this is the same saying, negative differentiating, and to differentiate f of s, which is that, remember b is a constant, s is the variable. We can write this as the following. Put this up here with a negative 1 exponent, the calculus stuff, right? So we can write this as b times s squared plus b squared to the negative 1, like this. Pretty nice, huh? Now, of course, bring the power to the front, minus 1, and then let's write it down. Negative times negative is going to give you positive, so that's good. And then we'll just have b parentheses s squared plus b squared to the negative 2 power. And of course, don't forget your chain rule. Multiply by the derivative inside. Derivative of 2, that's the answer. Derivative s squared plus b squared is 2s, like this. And now we can, of course, just put everything down together. This on the top, so we have 2s with the b on the top. Again, this is the s, right? S. Over this right here is the parentheses s squared plus b squared, and then raised to the square power on the bottom, like this. So this right here is the Laplace transform of t times sine of bt, right? Just like that. Very cool, huh? And now, as an extension, what if you multiply by t squared? As I said, just go ahead, just extend the idea. If you have t squared here, you do the second derivative, and you multiply negative 1 twice. If you have t third power, just go ahead and do what? Differentiating 3 times, and then you multiply by negative 1 to the third power, and all the good stuff, right? So that's pretty much it for number 16. And I would actually like to go back to number 14 for you guys a little bit. I erased that. It's not good. Actually, let me just put down what I have right here on the notes. I wrote this down as honorable mention. So for that idea, so this is just the honorable mention, right? Honorable mention. Yeah? Well, the idea is that if you have the Laplace transform, and originally if you have the function right here already, yeah. But if you have to multiply this with t to some power, and assuming n is just from 0, 1, 2, 3, 4, 5, and so on, and maybe later on you can do some like fractional derivative, but that's later on. Anyway, though, This right here, all you have to do is the following. First, look at what Laplace transform of f of t is. As a result, we'll just write it as f of s. Yeah? This is t to the nth power. All you have to do is do the nth derivative in the s world, like so. Right? Do the nth derivative in the s world. So let me just write this down nicer for you guys. D to the nth power over dsn, like that. But you see, each time you do the derivative, not only you do the derivative, but you also have to multiply by -1. Yeah? So you actually have to do -1 raised to the nth power. Just make sure that you have the right sign and all that stuff. All right, so this is my honorable mention for you guys. This just doesn't look nice. Sorry. -1. Better, maybe. All right, so this right here is just an honorable example. No. I'm not doing the derivative. I'm going to do the following. The Laplace transform of t to the third power e to the 2t. Does this look familiar? It should. That's question number 14. Anyway, earlier, the way that we did it is we took this as f of t, right? That was actually the easy way. Now, I'll show you guys the hard way to do this. Now, I would like to take this as my f of t, the little f of t, and this is t to the third power. Because here we have t to the third power, so that means I will have to multiply the -1 3 times, and then I will have to find the third derivative, which is the jerk in this case, the third derivative of the following. Well, let me just remind you guys. Let me write it down right here. If you look at the Laplace transform of e to the 2t, if you just look at this part only, the a value right here is 2. So this right here is 1 over s minus 2. S has to be greater than 2, but you don't need to write that down too much. And this right here is precisely our f of s. So this right here is the f of s. All right, so you do the third derivative of f of s, which is just the 1 over s minus 2, like this. But again, if you want to do the derivative of this, it's easier if you write it as s minus 2 to the -1 power, and then just enjoy your derivative. All right, here we go. The trick is to do this carefully with the negative signs. Here, you get -1. Do the first derivative, so I will have just d2, ds2, right? Do the first derivative right here. I'll bring the -1 to the front, -1. The chain rule is just 1, so it doesn't really matter. So you get negative s minus 2, like this, and then -2, yeah, like that. So that's the first derivative. And then let's just have the -1 all the way in the front. Next, you do this again, put this to the front, -1. It's kind of fun. You lose one derivative because you just did one derivative already. Here you get negative becomes +2, and then you have s minus 2, and that's -3. And then what do you do next? Yes, you do it again, and that's the last one. Put this to the front, -1. So that's going to be -6 times -1. All in all, it's going to be +6. And then you have parentheses s minus 2 to the 4th power. And of course, we can write this down as 6 over s minus 2 to the 4th power. Like that. Right? Just like this. Very good, huh? And of course, don't do it this way. Don't do it this way. It's longer this way. You should take t to the 3rd power as your f of t, and then you do the shift, right? That's much better. But you know, I'll show you guys both, right? So no complaints. All right, so that was number 16. It's my honorable mention. Earlier we multiplied by t. This time we are going to differentiate. We are going to divide it by t. God, and you can expect that we will be getting integrals, of course. So let me just write this down right here for you guys. Right. So number 17, but let me actually write this down right here first. Again, Laplace transform of t. Actually, let me write this down because it's really cool if you put it down like this. First, Laplace transform of f of t. This is just f of s. Good. And as we all know, if you have the Laplace transform, if you multiply by t of f of t, this right here, all you have to do is you differentiate in the s world of that. So you have the capital F of s right here. But don't forget you multiply by -1. And now, have you thought about what if we have to divide it by t? So let's go ahead and do calculation number 17. Here is the question. What's the Laplace transform of f of t? Let me put it down on the top. And then we divide it by t instead. Yeah? So what will we get if we do like that? Well, this is like t to the -1 power. It's just that you do the integral, huh? Yes, I agree. But we have to do it carefully because you cannot just integrate f of s, because if you do this, you forgot the constant, you forgot the ds. Well, no, joke aside. If you do this, you may end up with some constants, yeah? Because this is an indefinite integral. And maybe you say, maybe you just go from 0 to infinity. That's actually not true. So you have to do this one carefully, and this is how. So have a look. Let me write down the definition first. This right here is the integral going from 0 to infinity. And we still have e to the -st. And all this, I'll just put it down right here for you guys in red, f of t over t, like so. And then we have the dt. So that's exactly what we have, right? Let's think about it. This is the f of t. And then we have the f of t here. How did we prove this earlier? We differentiate this, yeah? We differentiated that with respect to s, right? We use the Feynman's technique, or the Leibniz rule. Derivative of e to the -st. That's how we can produce an extra t. That's how we get that, right? This time, we want to divide. So maybe it's this guy again. But I'm not going to differentiate. I should be integrate, because if I integrate e to the -st, I will have to get what? I will end up with divided by this, right? So that's the hint. And I will just have to make some observation. And perhaps let's do the following. Let me put this down right here. So first, put down some observation, right? If we integrate e to the -st, right? Just integrate this part. Well, what's the answer for this? This is going to be e to the -st. That works. That's great. But the reason I have put down dt or d whatever, it's because of the following. I'm trying to produce the over t on the bottom, so I'm not going to integrate this in the t world. Instead, I will be integrating this in the s world. So ds that. Why? Because in the s world, t is the constant. So when I do this integral in the s world, we will have to divide it by -t. So I actually end up with 1 over -t, like this. So we have to integrate this in the s world. Yeah? Really carefully. Be really careful on that. So that's nice though. But the problem is that I will still end up with some bizarre things, because I will have the constant plus c, for example, right? So that's no good. So we should somehow use a definite integral to help us out. So maybe it's a good idea to still have infinity, because if you have the infinity, put it here, and you just need to write down s has to be greater than 0, and that will become 0. That's nice. But I want to end up with Well, let's see. Should I just integrate this from 0? No. Actually, I'm integrating this in the S world. I get that, and then t is the... No. Can I put this down in the 0? If I put down 0, again, we're integrating in the S world. I will have to put a 0 in here. Sorry, I should have said the infinity is for the S right here because we're doing this in the S world. If I put a 0 in the S, that part goes away. I don't have the e to the negative st anymore. So be really careful. I actually have to integrate this from S to infinity. Check this out. Right? So again, let's integrate e to the negative st from S to infinity in the S world. So of course you do our integration and we got that. And then what we'll do is we have to plug in, and I will just go ahead and plug in this in black, I would say. Plug in, S to infinity. But the idea is that, again, we are doing the S world. Okay, now here is the bizarre part. You can plug in S is equal to S is equal to infinity. The problem is that nobody does that. Some people are okay with that, but some people are not. What you have to do is, right here, instead of using the S, you will have to change that to a different variable. Because the dummy variable and that cannot be the same. And the problem is that at the end, you want to end up with the S. So you just have to change the S earlier. So earlier, I will just have to change all the S inside here to be U. Just say that U, and then I will do the same right here. This is still going from S to infinity. That's good. But now this S is actually U. And again, this is just how you can be slightly technical. And this is, again, just the observation that we're making. I don't want to tell you guys, hey, just do that and then you will get the answer. But this is the thing that you have to do a little bit on your own sometimes to make sure that you can actually get this to work. But anyway, let's continue. U is infinity here, you put it here, and of course t is greater than 0 because originally this right here, t is going from 0 to infinity. So that will take care of the business. You put this right here, the first part will be 0, and then you will have to minus. You put s right here, so you end up with 1 over negative t, and then you have e to the negative, you put s right here, okay? st, like that. And all in all, you end up with e to the negative st over t. This is so wonderful, isn't it? Because now, this portion, you can just have an integral inside. That's the idea. All right, so what exactly do we have to do with this though? Let me show you. So this is the observation. It took us a while, but now this is what we know. Again, let me just write down the original. Let's see, where is that thing? We know this, yeah? So we know the integral of, the Laplace transform of f of t is equal to f of s. This is what we know. Now, for this right here, I can change that to the definition, namely the integral from 0 to infinity, e to the negative s, right? T, and you have f of t, and you have the dt like this. And this is equal to the integral, and you can have that to be the s and all that. But really, we want to integrate, and we have to change the dummy variable to be u. So, again, this variable and that, they will match. So instead of putting down s right here, I will actually use u. And then right here, I will actually have f of u. And this right here is actually du, because we have to integrate this in the u world. And then, no, sorry. Not integrating yet, because the Laplace is already a, all right, let me do it again. All right, this is what we know, yeah? So let's put down the definition of Laplace transform f of t first, which is the integral going from 0 to infinity e to the negative s t, and then you have f of t dt, and that's equal to f of s. Yeah? So this is just the definition, and of course the right hand side is still s. Now check this out. This s and that s are the same, but in fact we're about to integrate, and we still want to end up with s to be nice. Yeah? So instead of having the s right here, I will change that to be u. To be u. And again, this is just a dummy variable. You could have used whatever you want and all that stuff, right? Now, what we are going to do is, we are going to do what we did right here. We will integrate both sides from s to infinity. So right here, I will integrate this from s to infinity, and then from here, I will also integrate this from s to infinity. And again, you see the output of the integral in black would be in terms of u, so I will have the du right here. Likewise, the output right here will be in terms of u, so this is again in the u world like this. All right? So now, here is the deal. We end up with a double integral. But it's not so bad at all, because if you look at the t and also the u, I will write this down right here for you guys. Let's say this right here is the t-axis, and this right here is the u-axis. Yeah? Can we see okay? Okay, first of all, t goes from 0 to infinity, so it's just this portion, yeah? And then u goes from s to infinity, and let's say s is somewhere right here. So the region that you're talking about is just this part, so it's just like a rectangle, yeah? The best part about that is that we can just switch the order of integration, and that's very nice. And let me do that for you guys. Let me do the integral from 0 to infinity, and then the blue integral from s to infinity, and we'll have the du first, and then we have the dt after that. And for the inside, well, I really want to have this to happen, so what I will do is, let me just write this down again. Let me just write down everything again. So inside here is e to the negative u, and we have f of t. Inside here, we have e to the negative u, and then we have f of t, like this. Now, the right-hand side is still equal to the integral from s to infinity, f of u du. Okay. On the left-hand side, have a look. We are looking at the u world first. That means f of t is just a what? It's just a constant. So you can put that right here. Cannot put it all the way in the front though, because you have to deal with that in the t world. So have a look. All right? So let me put this right here. So we have the integral from 0 to infinity, and then the f of t right here. And then we have the, actually, let me just put the f of t in black. So we have the f of t right here. And then we have the integral from s to infinity. And then we have e to the negative ut. E to the negative ut. Just copied it wrong. E to the negative ut. And then du. And dt. Right? And now have a look. We know this right here is equal to this. Is the integral from s to infinity of f of u du. What's this in blue? This is exactly what we came up with earlier. So I can just put down the result right here. I'm not going to work that out again. You can just look at that. So we actually have the integral going from 0 to infinity, and this is f of t. And then we have this for the whole thing. So we have that with e to the negative st, right? So now we actually end up with this. So that's why it was really bizarre earlier, but that's one of the things we have to get used to. Anyway, this is equal to that, and we have the dt. What's this? This is exactly what we are trying to find. Yeah? So I'll just put this down I don't know, it's like a triangular equal sign. But anyway, finally, I'll write this down right here for you guys. This is telling you that the Laplace transform of f of t, if we divide it by t, right? If we divide it by t, because this right here represents that, this is equal to the integral going from s to infinity of f of u du. And this right here is it. Very nice, huh? So you can see our assumption was correct. Earlier, when you multiply by t, you differentiate and multiply by -1. And you just have to do it carefully. When we divide it by t, we actually integrate, but you have to do it from s to infinity. And you don't actually multiply by a negative whatsoever. Huh? So have a look, have a look, have a look. Pay attention to the observation, especially that part. And it's just how we can make things happen. That's what I like to tell you guys. All right, so I'm going to leave this on the board just to remind you guys, because for the next one, it's going to be an example. I can figure out crazy Laplace based on that. All right, so of course, let's go back to black pen, red pen, even though I use blue sometimes. All right, number 18, right here for you guys. Number 18, here, let's look at the Laplace transform of sine t, just sine t, all right? And then I want to divide it by t. Oh my God. Right? First thing first. Perhaps I will write it down right here. We know that what's the Laplace of sine t? This is just sine of 1t, yeah? So it's 1 over s squared plus 1. That's what we know. And again, we are about to integrate, so I'm not going to use s. Instead of the s right here, we'll just change to u, right? So here we go. Because we're dividing by t right here, all we have to do is we will be looking at the Laplace transform of sine t, which is this. Let me write down 1 over u squared plus 1 for you guys. So this right here is our f of u. Yeah? And then you go ahead and integrate from s to infinity. So you look at this and you integrate that from s to infinity. And you are in the u world. And how can we continue? Just do the calculus, of course. All right. So what's the integral 1 over u squared plus 1 in the u world? Inverse tangent. So for this, we just have the inverse tangent of u. And then we plug in s and then infinity, all that stuff. Plug in infinity. Inverse tangent of infinity is precisely pi over 2. And let me just write down everything for you guys. Inverse tangent of infinity. And then minus, let me just do like this, and then minus inverse tangent of s. Yeah. This right here is what? Pi over 2, as I said it earlier. So we get pi over 2, and then minus inverse tangent of s. Look at that. How cool is this? Yes, this is the Laplace transform of the sine t over t. Very, very nice, thanks to this formula. Some honorable mention, right? This is number 18, and then I'm almost done, but some honorable mention. Right? When you have that, you can actually end up with some very nice integrals. Let me show you. Remember, what's this? This right here, it's the same as saying integrating, and just look at the whole thing inside as your function. This represents the integral going from 0 to infinity, and we write down e to the negative st, and we have sine t over t dt, like this, right? Now, with this being done, you just have to tell me an s value You can put it here, and you can come up with a lot of cool integrals. So let's see, what's the value of, let me just tell you guys, honorable mention number 1. What's the value of the integral from 0 to infinity of sine t over t then? Well, this, compared with that, this is the case when s is equal to 0. So all I have to do is tell you guys s is equal to 0, and then put 0 into here and then work that out. So this right here, it's going to give you pi over 2 minus inverse tangent of 0, and that's 0. So all in all, we end up with pi over 2. Very nice, isn't it? And of course, you can come up with another one, such as what's the integral from 0 to infinity? If you end up with something else that's crazier, let's say, let's do this, e to the negative t, e to the negative t. Actually, let's just do it right here. And then we have sine t over t dt. What's this then? Well, in this case, s is equal to 1. And can s be negative 1? No, be careful though, right? If s is negative 1, this won't converge, so this wouldn't make sense. So you still have to do this with caution. If you do that, be sure you have to make sure the s has to be positive. And so let me just write this down here for you guys. S has to be positive. But anyway, let's not ruin the fun. S is 1 in our case, so we're just plugging 1 into there. So we get pi over 2 minus inverse tangent of 1. Well, what's the inverse tangent of 1? Well, here we have pi over 2. This right here is minus inverse tangent of 1 is just pi over 4. And get our common denominator, 2 and 2. So, you know, it's 2 pi minus pi is pi, and 2 times 2 is 4, and that match, so it's just pi over 4. So, yeah, we have another one. Very cool, huh? So, thanks to this formula, it's so cool, isn't it? I have another one for you guys. Number 3, honorable mention. So, let's look at the integral from 0 to infinity. Actually, let's do it like this. Let's do negative infinity to positive infinity. And here, I would like to ask you, sine of e to the x. Oh my god. Hey, this does not look like any of that. How can we do this? Well, do our usual calculus stuff. Let's do some substitution, yeah? So, have a look here. Maybe let's do some use up. Let u equal to the input function, which is e to the x. And you see du is the same as e to the x dx. So that means dx is the same as du over e to the x. Don't worry. You see, after the substitution, you see that's du over u. So if you put it back, have a look. In the x world, x goes from negative infinity to positive infinity. Take this integral to the u world. Well, when x is negative infinity, put it here. E to the negative infinity is nicely equal to 0. Put infinity to here. E to the infinity is infinity. So u goes from 0 to infinity, like that. Okay, inside here, we have sine. This is our u, so we have sine u. Dx is du over u, so I can put down du over u. Does this look familiar now? Yes, it does. It's just nicely equal to pi over 2, isn't it? So, and as you can see, this is the reason why we said the dummy variable doesn't matter, because the output is just going to be a number. So you see t, t, and t, u, u, and u, and as long as the limit match, this right here is the same as that, which is pi over 2. Pi over 2, very, 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 very nice. All right? So some really cool stuff if you know some Laplace transform, some very nice integrals that you can also do for free. Very good. All right? So let me finish the things, and then perhaps I will give you guys my other honorable mention later on. But perhaps I can tell you. See, if you have cosine though, right? If you have cosine t over t, in fact, that Laplace does not exist because the integral is actually divergent. But if you have 1 minus cosine t over t, that actually will give you a convergent integral, and you actually get a nice one as well. I will do that all the way at the end, just like a little bonus. But this is really cool already. All right, we are going to be taking Laplace transform of a derivative. So have a look here, number 19 on the board for you guys, number 19. Here we have Laplace transform of f prime. So it's no longer just the original, it's the derivative. All right, all right, all right. How can we do this? Use definitions, of course. So here we go. This right here, by definition, is the integral from 0 to infinity e to the negative st times f prime of t, and then dt right here. Very nice. But it's not so nice, because how can we deal with this improper integral? That's the derivative. Well, I want to have the original, because if I have the original, we know that's just the original, capital F of s. This is f prime. So how can I give to f of t from f prime? We have to integrate this guy, yeah? You see, we have to integrate just one part inside of the integral. So what should we do with that? Go ahead and differentiate. One part to be integrated, the other part to be differentiated. So what should we do? Yes, integration by parts, and yes, DI method. So have a look. Oh my god, this is so much fun. D and then I, and then I'll put down the plus minus. Just 2 rows is enough. Don't go too crazy, of course. We want to integrate f prime of t, because if we do that, sorry, that's a horrible f. Because if we do this, we'll just get the original f of t. Very nice. And of course, in the meantime, let's differentiate e to the negative st. And don't forget, we're in the t world, and don't forget the chain rule. The derivative of e to the negative st is e to the negative st, and the chain rule says multiply by negative s, because negative s is the constant. Multiple with the t is the variable, just like that. All right, now first part is just this times that. So this is equal to this times that, which is e to the negative st times f of t. This is the first part of the answer, but remember, this is a definite integral, so go ahead and plug in from 0 to infinity. Yep. And then we have to minus. We still have to do the product right here, and this is still going to give us an integral. So we have to actually do minus times minus, so it's actually a plus. So I'll just put down minus times minus. This minus in red first, times that minus in black, so it becomes a plus. Very cool, huh? Anyway, and I'll put everything inside of the integral. So you have the integral, and then I'll put this and that is e to the negative st, and then we have f of t dt, and this is still going from 0 to infinity. And you might be worried about that I didn't put on the s. Well, I can put on s here, but since it's in the t world, s is just a constant. Allow me to put on the s in the front, right? So have a look. The hardest part to teach Laplace transform is to write the s. Anyway, put the s in the front, so that's the s in blue, right? Now, we know a few things. First, when we plug in infinity to this right here, because in the beginning of the video, which is about 2 hours ago or so, I assume that f is with exponential order. So that means if you put infinity to this, it will be 0. So I will just have to write this down again. I will put this down. F of t, suppose it has exponential order. So when we do that, the first part will be 0, right? So that's nice. Then, of course, that's the first part. We are going to minus, put the 0 into here and there. So we have, the rest is just e to the negative we are doing that in the t world, so you put the 0 into the t, so it's negative s times 0, and then times f of 0, like so, right? And then we add, again, here is the s. But what's this part? Actually, hold on. This is the s. There we go. What's this part? This is our definition of the Laplace transform of little f. Very nice, huh? This right here is nicely equal to capital F of s. Of course, you can, if you would like, you can still write the Laplace of f of t, but you know they are equivalent anyway. And we're almost done. Just to clean things up. Notice this is just what? 1, right? And this is minus f of 0. So be sure that you do the following. And how did I write it? Oh, yeah, I write it down like that, so okay. So I will fit in everything here. Finally, we have the s, f of s, minus little f. So you have to refer back to what your little f is, right? So you should look back your functions. And usually you do this when you're solving a differential equation, initial value problem actually. So usually this would be given, and you have f of 0. That is for this, and we are done. Very nice. Right? And again, f of s, if you would like, this is the Laplace transform of little f of t, like that. All right, so that's it. Now, after the first derivative, what should we do? Sure, let's go ahead and do our second derivative. Let's see, number 20. Laplace transform. I want to figure out what's the second derivative. We can do this again and just have to integrate, twice, right? So you have 3 rows, all that stuff. But life doesn't have to be that hard sometimes. We have that already, so we can use that. Make good use of our results. So this is how we are going to do it. So I'll put this down in blue. First, this is what we know, right? So have a look here. We know that the Laplace transform and f prime of t, let me write it down like this. This is the same as saying we have f of t, right? And then we differentiate that. That's how we get f prime of t. Good. And this is equal to, well, you see f of s is equal to that, so let me put this down right here for the f of s. Yeah? So this is equal to s in the front, and then f of s is the same as that, so that's why I purposely wrote it down over there. And then the input here is f of t, very cool. And then in the end here, we have little f of 0, and that's a minus little f of 0, just like this. This is what we know, and now let's make the best use of this. Now, what's the connection between second derivative and the first derivative? Yes, you just differentiate the first derivative again. So have a look. So now, if you want to get the second derivative, let me write it down better for you guys. Sorry. Now, so let me just literally put down now. If you have the Laplace of the second derivative of t, like this, right? This is nicely equal to the Laplace transform. You just have to differentiate the first derivative. So as you can see, all I did is just rewrite this. F double prime is the same as f prime, and then prime that again. Yeah. Now check this out. F of little t, little f of t, little f of t, little f of 0. This, and that, they are the same kind. Now, my kind right here is f prime. So next, all I have to do is the following. Here, I still have s. And then I will just do the Laplace. And then this is just going to be this. Yeah? So I'll put down f prime of t. Very nice, huh? And then minus, instead of f, we put down f prime. So we have f prime of 0, like that. And this is so wonderful. Have a look. This, and that are the same. Very, very nice, isn't it? Now, do we know what this is? Of course we do. It's the same as that. So, we know the following. I'll just put this down for you guys. This is equal to the following. S in the front. But for all this part, we can just write it like that, which is with a parentheses. And then we have the S, capital F of S, minus 0. So this is for that. So F of 0. Yeah. And then in the end, we have that minus F prime of 0. Now, finally, we just do some work. And usually, we put down the F prime first before that. And that's why I did. Actually, I didn't do that. Never mind. So I will just write down everything for you guys. You distribute the S. You have S squared F of S minus S little f of 0 and then minus F prime of 0. Like this. Congrats! This is our Laplace transform of the second derivative of some function. Just like that. Very cool, huh? So just put this down here. Okay, so 20 Laplace transform done, and then 4 more to go. So earlier we did the first and also the second derivative, and now what should we do? Yes, we should do the integral. So number 21, right here. The best form, right here. So number 21. Let's go ahead and do the Laplace transform. And inside here, be really careful, is the integral going from some number to t, right? Sorry, it's from 0 to t. So you have to do it carefully. This is the integral going from 0 to t. And then here, I'm using phi as my dummy variable. So I have f of phi, d phi, and then that's equal to, what? I don't know. Yeah. Can we use this again? Can we use this again? I think so, because derivative and integral can cancel. Have a look. So let's do what we did earlier. So let me write this down right here for you guys. This is what we know. Earlier, when we do the Laplace transform of the derivative of some function, and I wrote it down like this, right? This right here is equal to S times the Laplace transform of f of t, and then minus f of 0, like that. Yep. Now, have a look. This is my input. Let's go ahead and put this into here, here, and also here. Well, how do I do that? I will show you, don't worry. So, our function here, I will change it a little bit because the notation is going to be, this has the f already, so that's not good. Let me actually put down g if you don't mind, right? Yeah, because in our case here, this right here, I'll just call that to be g of t. And again, this is not like capital F or whatsoever, because capital F is reserved for the output of the Laplace of little f. So that's why I'm using g. So in this case, I will just say, let me see why I can put that down. So in this case, I'll just say let, right, g of t be that. And again, you integrate whatever little f is, plug in 0, plug in t, the output is with t. So g of t, and you get the integral from 0 to t, f of v dv. And of course, let's go ahead and plug in into everything. So we're looking at this right here. G of t is just that integral, so it's just what we are going to do. Integral from 0 to t, f of phi dphi, prime that, and then close that, and then s, Laplace transform of the integral going from 0 to t, and then we have f of phi dphi, good, minus, and, oh sorry, this right here, I'm using g, so this right here should also be g, and it should be g of 0. Okay, the reason that I write this down on purpose, I wrote down g of t like this on purpose, is because g of 0 is this. Well, all we have to do is putting 0 into the t. You see here is where the t is. I just have to put down 0 right here. So g of 0 is actually integral from 0 to 0 of that f of phi dphi, and that's nice d equal to 0. So this is legitimately equal to 0, which is very nice, right? So I just want to show you that this part goes away because of how we have it there. Well, how do you take the derivative of this? Derivative and integral cancel by the fundamental theorem of calculus, part 1. So have a look. The left-hand side, they cancel. You put a t right here though. Okay, you put a t inside here though. So you actually end up with f of t, and that's it. Right? That's it. And then on the right-hand side, of course, you have the s times the Laplace transform of the thing that we are looking for. So we have the integral going from 0 to t, f of phi dphi, like this. And finally, what can we do? Write down the answer, of course. I want to figure out this. All I have to do is divide the s on both sides. So finally, Laplace transform of the integral from 0 to t, f of phi dphi, this is equal to the Laplace transform of f of t. And then on the outside, right, on the outside, you divide it by s, so you can put this over s. And of course, if you would like, you can write it as f of s divided by s. Up to you, whichever one that you like. So one way or the other. Just like that. Very cool, huh? Now, next, it's another Laplace of an integral with a star. That's a new kind. It's a special kind of integral called the convolution. Pop quiz for you guys. Do you guys know what does the word Laplace mean? If you know, leave a comment down below. Right? And question number 2, what does the word convolution mean? If you know, leave a comment down below. All right, so number 22, right here. Here we go. Here we have the Laplace transform. And the input here is what we call the convolution, namely f of t, and you do the star right here, and with another function, g of t, like that. Now, here is the idea. This is actually not regular multiplication. If you have a Laplace transform of 2 functions, the functions have to be special enough, like the ones we have done, either e to the at or t to some power, so you can end up with nice formulas. But if you just have general functions like Laplace transform of ln t times sine t or whatsoever, there's no product rule for the Laplace, unfortunately. However, if you have the convolution inside, it's a different story. You actually end up with something extremely nice in this case. I'll show you guys what that is. But of course, the first thing is to tell you guys the definition of the convolution. So I'll write this down right here. This is called the convolution. Spelled it this way, I hope. Okay, let me just. This is called the convolution. And again, f of t star g of t. By the way, that's called a star. That's why I say star. This right here, it's an integral. It's an integral going from 0 to t. So it's kind of similar to the one that we did earlier, okay? But not exact. Inside, you have f of t minus the dummy variable phi, and then multiply. This is the regular multiplication. And then g of v d phi. So, just for fun for you guys, right? Just for fun. Question for you guys. What's 1.1? Huh? Question 2. What's 1 start 1? Huh? Leave a comment down below and let me know if you know the answer to that. In fact, yeah, if you have seen my videos in the past, thank you so much, right? So I did that in the past, so I will include the link to the video in the description for your convenience. Oh my god, man. This is not funny. Because Laplace is an integral, and now we're putting another integral there. We'll try our best. First, Laplace transform is the integral going from 0 to infinity, e to the negative st, yeah? And then we'll put this inside, and I might as well just put down the definition right here already. So I will have the integral going from 0 to t, and then we have f of t minus phi, and multiplied by g of v d phi. So this is the convolution. And then on the outside, we still have the dt. It's okay, it's just double integral. Let's see what we can do. First thing first, when you go from 0 to t, you have a t over there. We don't like that. We prefer to have rectangles, right? So that we can just change the order of the integration. That's much better. If you want to change the integration right now, leave a comment down below how you get it, but I'm not going to do that. Now, I will like to have this going from 0 to infinity as well, because so that we can actually end up with a really nice Laplace for the function f and also for the function g. You will see. But how can I make that happen though? One hint right here is that we have f of t minus phi. Have we seen the t minus phi as input already? Yes, we have. Where? Yes, the unit step function. So let's see what we can do with the unit step function, right? Well, in our case here, if you would like, you can, let's see, how should I, let me just focus on the red part right here. So I am just going to graph this part right here, just the red part, right? So I will just do it in red and blue. Okay, so I will give you guys a picture right here. Suppose here we have f of t minus phi times g of phi. So this is our function in red, and here, remember, we are in the phi world, so phi is the variable. I don't know how it looks like. Let me just give you a sketch. So maybe it looks like this. I have no idea, really, right? So let's say this is how the function looks like. Now, here is the deal. I would like to multiply by the unit step function. Well, phi is the variable, t is the constant. And let me just remind you guys, when we have the unit step function, this time though, because they both look like variables to me, so I've already done like this. When we have a number, sorry, let me do it like this first. When we have a variable minus hashtags the number, right? Just easier that way, right? This right here produces the following. Whatever the number is, right? This is whatever the number is. Anything before the number is 0. Anything after that, it jumps to 1. Right? So this is how it goes. If the inside is positive, it's 1. So variable greater than the number is 1, so just like that. However, if you have the unit step function, if you have the number minus the variable, this will give you the other direction. So what that means is that anything, so let's say here is the number. Here's the number in red. Anything before is 1, and anything after that is -1. So be really careful with this. Now, here is the deal. Pay attention to the red integral. We are just going from 0 to t. So with this picture right here, we just want to go from 0 to t. And again, t is our number in this situation. And that's the integral That's the area for that integral. That's all we need. We don't need anything forward. So we actually have to multiply by this kind of situation. But it's actually so wonderful because you notice that t is the number. V is the variable in the V world right here, right? So have a look. If we have this, so I will just put it down in blue. If we have f of t minus v, g of v, and we multiply by u of t minus v. And again, this right here is the variable, and this is the number. So when I multiply this with the function here, what happens is that anything before it maintains. So the blue portion is, right here, still maintains. And anything after that becomes 0. And 0 times that will just give you 0, like this. So the blue portion is for the blue function right here. So what I'm going to do is, I can multiply by u of t minus v, and then to get the same area, we can actually just go from 0 to infinity. Everybody happy. So know this idea right here really, really well, right? So let me erase this because we will for sure need more space. All right, first thing first, copy down the things that we have. So this is integral 0 to infinity. Here is e to the negative st. And then this is the integral going from 0 to something that I need not put down yet. I'll write this down again, f of t minus v, g of v, and then let me multiply this by u of t minus v, because I'm doing this because I multiply by u of t minus v, from t and onward it's 0, so I will change that to infinity. So that's really, very nice. And then just continue. We have the dv, and then we have the dt, and everybody happy. Right? Now, perhaps we'll just clean things up a little bit. I will do this in black and red. I will first put this inside, and then we'll switch the order of integrals. I will write down this in 2 steps, right? First, integral in black, and then integral in red. They are both going from 0 to infinity. I'm just going to put this inside. So we have the e to the negative st, and then we have the red part, which is the f of t minus v, g of v, and then of course, let's keep the blue, of course, u of t minus v, and then we have the dv, and then we have the dt, right? So I'm just putting everything inside. And now I will switch the order of the integration. Well, with that being said, the red integral will go first, from 0 to infinity, and the integral in black will go next. And then I will still write down everything inside again. Actually, no, let's do this in your head, right? So let me put the red integral on the outside. So we have this, and then we have the dv on the outside, right? And then I will have the dt. So we have the integral from 0 to infinity like this. Now we have everything right here. You can put it down right here, but in the t world, hey, g of v is a constant, so we can put that to the front. This right here has to stay because it has the t. This and that, they also have to stay because it has the t. So I can put the g of v in the front right here. Sorry. Let me put the g of t first. G of v, and then the integral from 0 to infinity, and then the rest I'll just write it down in black. E to the negative st, and then this is f of t minus v, and then u of t minus v. T minus v, like this. And then I'm doing the dt first, and then the dv after that. Just like that. Very cool, huh? Unit step function, and I think we have done this already. Yes. Have a look. Here we have the integral in red still, that's 0 to infinity, and this is g of v. Good. What is this? This is the Laplace of this function, isn't it? Yes, it is. So you can write everything down right here as the Laplace transform of f of t minus v, u of t minus v. And then on the outside, we have the d phi. Oh, I should stop using my hand, otherwise my hands are just going to get really dirty. So this is what we have. Very nice, huh? Now, let me just go right here. All right, so in the front, we still have the red integral going from 0 to infinity, and we have g of v. Do we know the Laplace of this? Yes, we do. Well, in this case, though, v is a constant in black, because in the black right here, t is the variable. So v is the constant. So it's pretty tricky. So be sure you just kind of keep all these little things in mind. So we have the f of t minus v. Yeah, v is the constant. Earlier, we were doing f of t minus a times u of t minus a, yeah? And what we get is the following. We get e to the negative v. And then you have the s. Yeah, and then we have the rest is just f of s, right? Because the input match, so you just have this right here. And again, I'm just using phi instead of the a. So same thing. And then on the outside, we still have the dv. Ah, so nice, huh? Because now f of s is just a constant in the phi world. I know, it's just really crazy, but it's really fun. You can put the f of s all the way in the front, and then look at the red part. So here we have the integral going from 0 to infinity. And allow me to write this down first, which is e to the negative phi s. And then this right here is, actually, let me write it as SV. Yeah, let me write it as SV. And then write down g of phi, and then we have d phi. And do we recognize what this is? V match, and then it goes from 0 to infinity. This right here is precisely the Laplace transform of the g function. So finally, we can just write down f of s and regular multiplication of capital G of s, like this. This is so wonderful. And of course, if you would like, you can write it down as the Laplace transform of little f of t, little multiplication, right? Just the regular multiplication. You can put a little dot if you like. And this is just Laplace transform of little g of t. Like that. So one or the other. Right? Just like this. So cool. This is one of the most wonderful Laplace transform formula. And yeah, it's so nice. Right? All right. And again, don't forget to comment what's 1 star 1, right? All right, so let me show you guys examples. I'll just say this is number 23. I'll give you guys 2 examples. Okay, what's the Laplace transform of sine t, regular multiplication of cosine t, versus the other one, Laplace transform of sine t star, which is the convolution, and this is cosine t, right? Just like that. And in fact, I'm not going to say this is question number 23. This is just the honorable mention, right? So let me just say this is the honorable mention, right? So Laplace transform of sine t cosine. Oh, this is so not pretty. Sorry. Sine t cosine t versus that. All right, which one's easier? This one. Let me do this one first. This right here, it's a convolution. We can use the convolution theorem that we proved earlier. This is the same as saying, do the Laplace transform of the first function, and then you multiply by the Laplace transform of the second function, which is cosine t, like this. What's the first one? Well, this is just 1 over s squared plus 1 squared. What's the second one? It's just s on the top over s squared plus 1 squared. Final answer, s on the top multiplying, so it's parentheses s squared plus 1, and then square that. 1 squared is 1, right? So that's why I didn't put on square. Done. How can you do this? This is a regular multiplication. It's not as easy, but it's also still doable. So notice that, that's just some note right here for you guys. When you have sine cosine, you can look at the double angle formula. Sine of 2t, this is just 2 sine t, cosine t, right? Just like that. Very good. Now, here we have just 1 in front, so you can just divide the both sides by 2. So here is the deal. I will just write it down, right? So this right here is the same as saying the Laplace transform. I will divide it by 2, so I will have 1 over 2, and then we have sine of 2t. Just like that. It's the same. So use identities sometimes. Now, 1/2 is 1/2. Good. And then sine of 2t, well, we did this a few times already. B on the top, right? So we have the 2 on the top. And then over s squared plus 2 squared, like that. Hey, guess what? This and that cancel. Pretty cool. So, final answer, we get 1 over s squared plus 4. Cool, huh? All right, so this is how you can use the convolution, and you have to just really make sure if you have convolution or regular multiplication and all that good stuff. Now, just 2 more to go, so let's go ahead and do the following. 23. Laplace transform, and now here I have square root of x, right? This right here, it does have a Laplace transform, and I'll show you guys what the answer is. You can use the definition, and then you can do some U substitution, and then you can use the Gaussian integral, and so on, so on, so on. But I will take a shortcut right here, right? So I can just show you how you can extend the idea of the factorial. So, know the following. Remember, we know that the Laplace transform of t to some power n, this right here is equal to, well, pay attention to what the n is. This right here is equal to n factorial that divided by s to the n plus 1 power, like this. And the truth is, this right here doesn't have to be just 0, 1, 2, 3, 4, and so on. You can actually have a lot more numbers. This right here, if you would like, you can have the Laplace transform of t to the r's power. And I'm using r right here, and we will say this is r factorial over s to the r plus 1. In this case though, r has to be greater than -1. And what I'm going to do is actually the following. Not yet, I'm sorry. R, let's put that down, I'm sorry. R has to be -1, greater than -1. Right? So, no, not yet. All right. This and that almost identical, but for R, we are going to say we can actually use what we call the gamma function to extend the idea right here. So that's what we have, and another note is, let me just show you this right here. Oh yeah, so this is called the gamma function. Let me just put this down. Gamma function. And it's like a hangman, of course, like this, right? Gamma of some input r. This right here is equal to the following. Laplace is what? It's an integral. What's gamma? It's also an integral. You have the integral going from 0 to infinity. I'm not making this up. I don't know who did. Well, anyway, nobody did. It's legitimate math. So you start with t first, though, and then you do r, and then you have -1, and then you do e to the -t dt, like this. Right? So this is what we call the gamma function, and the good thing is that you can say the gamma of, and you can also have the pi function, but let me just use gamma right here. The gamma of r plus 1, which is precisely you put the r plus 1 in here and just work that out. And you can just say this right here is equal to n factorial, r factorial. Let me actually just write this down. 0 to infinity. And let me actually just tell you guys. T to the r. Plus 1 minus 1 just r, yeah? And then e to the negative t dt. And again, this particular one is also called a pi function, and it's just capital pi of r. Right? So I still end up with telling you guys the pi. But this is not a pi ab, it's just a capital pi function. And the very nice thing is that you end up with r factorial for this. Very nice. And again, in order for this to work, you should technically say r has to be greater than negative 1. Right? So just to make it slightly more legit. But anyway, you can do the following. R factorial is equal to this. So you can write this down as gamma of r plus 1. And then over s to the r plus 1, like so. Very nice, right? And the best part is that you can use this as your new definition to extend the concept of factorial, and you can end up with the following. If you have r is equal to 1/2, right? Then you get 1/2 factorial. And again, you can just put the 1/2 in here, and that's pretty much going to be the, that's pretty much how you're going to start with the Laplace transform of the square root if you want to do it with the definition. But I actually have a video on this, so you can go ahead and check that out. It's a famous result if you have seen it already. 1/2 factorial is nicely equal to square root of pi over 2. Right? So this is a very nice result if you use the gamma function. So with this being said, this is how we can do it. Now I'll just put this down right here. The Laplace transform of the square root of x. Sorry, no, not square root of x. I'm not using x, I'm sorry, I'm using t. T, square root of t. Yeah? This right here, of course, it's the same as saying the Laplace transform of t to the 1/2 power. And we can just put the 1/2 into here if you wish. So in another word, we can say this is the 1/2 factorial. Again, not in the usual sense. You have to use the gamma function to actually work that out. Divided by, though, s to the 1/2 plus 1. And now, based on what I told you guys right here, this right here, 1/2 factorial is just nicely equal to square root of pi over 2. Yeah? Square root of pi over 2. And then s 1/2 plus 1, it needs no introduction. It's just s to the 3/2, like this. So this is it. Yeah, this is it. So for this one, let me just tell you guys what the gamma function is. And then it actually works out very nicely. Pretty cool stuff, just like that, right? How long has it been? 3 hours, not so bad. My life goal is to run a marathon, 26.2 miles, under 4 hours. And my latest one, which happened 2 weeks ago, right, the LA marathon, the medal I showed you guys last time. Take a guess my time. Take a guess my marathon time. I post a picture on my Instagram and all that, so if you guys know it, you know it. But if you don't, you can take a guess. All right, question number 24. This is really sore right now. Question number 24, and then here we go. Laplace transform of, I start with an L, so of course, ln t, haha. Natural log of t, crazy stuff, huh? So, let's have a look. This is going to look like the integral going from 0 to infinity, e to the negative st, and then we have to have the ln t dt like that. How can we integrate that? You might do it a few ways. You can do this from scratch with integration like this and work it out. But I will do it with the gamma function that I just showed you guys earlier. And man, I forgot the gamma function. It's somewhere. Anyway, though, here we go. So this is what we know. So let me just put this down right here. And let me actually just start with what we had earlier. We know that, let me put it down right here. I need more space. It should be okay. We know that, just like what we did earlier, the Laplace transform of t to the r's power, I will put this down in red, why not? In black, why not? Just like this, right? This right here is r factorial over s to the r plus 1 power, but r factorial is the same as gamma of r plus 1. So I'll put this down as gamma of r plus 1 over s to the r plus 1, isn't it? Nice. And right here, of course, we can recall the definition of Laplace transform. This right here is the integral going from 0 to infinity, e to the negative st, and then we have t to the r's power, and then we have dt, and that's equal to this, of course. So gamma of r plus 1 over s to the r plus 1 power. Pretty good stuff. Now, compare this and that. I need to squeeze out an ln(t). Let's think about derivative, because we did an example really similar to this already, right? Earlier, if you want to squeeze out the t, we can just differentiate this with respect to s, so we can squeeze out the t. But now we want to squeeze out the ln(t). I'm not looking at this part anymore. I actually have to look at this part, because when we have t to the r's power, if we differentiate this with respect to r, then we can squeeze out ln(t), and that's very, very, very nice. So let me write it down for you guys. Let me just put down some notes right here, yeah? So recall that if you differentiate your function, let's say d dx, some number for the base, the jet base, to the x power, if this is the variable, then you get b to the x times lnb. Right? So just keep that in mind. So with that in mind, I will go ahead and look at this, and I will go ahead and differentiate this with respect to r. Yeah, just like that. And technically, I should put on the partial, but I will do that inside. Anyway, so here we go. I'm going to differentiate both sides. This is like a function in terms of r, s is the constant anyway. So when I put this on inside, that's the time I will change that to partial. 0 to infinity, and then we have the partial with respect to r, and then the inside is e to the negative st, t to the r, and then we have dt. And then again, the right-hand side, we'll just go ahead and do our usual derivative. Let's say the s is the constant we know already. Anyway, here we have the gamma of r plus 1 over s to the r plus 1. All right, here we go. This is just a constant, so it will stay. We will have the integral going from 0 to infinity. This is staying, so it's just e to the negative st. Yep. Then the derivative with respect to r of t to the r, we get this. So I'll put everything down in red. We get t to the r times ln t, like that. And then we have the dt. Very good. Now, the right-hand side, just go ahead and do the derivative by using the quotient rule. Because on the bottom and on the top, they both have r. So now here's the deal. On the bottom, I will have to square it. So s to the r plus 1, and then I will square that. And then on the top, I will put down the first function, on the bottom function. So it's s to the r plus 1 times the derivative of the top. And for now, I will just write down gamma prime of r plus 1. What's the chain rule says? The chain rule says multiply by the derivative inside, but the derivative of r plus 1 is just 1, so it doesn't matter. Then you continue minus the top function, which is, oh man, gamma of r plus 1 times the derivative of the bottom with respect to r, yeah? So you first repeat s to the r plus 1 and times the derivative of this, which is again just 1, so it doesn't matter. So this right here is what we have, right? This is what we have. Now, compare this and that. What can we do? I can just make r equal to 0, and we'll get what I get, yeah? So I would just say, let r equal to 0. In that case, the left-hand side gives us the integral from 0 to infinity, just e to the negative st, and then ln t dt, which is exactly what we are trying to get. Now, on the bottom here, we have s to the 0 plus 1, just s1, and then to a second power. All in all, we have s squared on the bottom, good. Put 0 in here, we have s to the first, good. And then we have the derivative of the gamma function at 1. And then minus gamma at 1. Oops, let me just make it one more artistic. And then over, and then times s to the first power, like this. So that's pretty good. Now, what's gamma prime of 1 and what's gamma of 1? Okay, so let's see. Put this down right here. Note. So remember, gamma of, and because we're talking about functions, so perhaps I'll talk about x, yeah, or r, whatever. Actually, let's just put on r because that's what we did earlier. So gamma of r. Yeah. Earlier though, we said gamma of r plus 1 is equal to r factorial, right? And you can see that I can just put 0 into that, so this is actually pretty, let's do this first. No, let's just do this first. Why not sometime? Okay, anyway, I'm sorry. Note, gamma of r, the definition of gamma is going to be the integral from 0 to infinity t to the r minus 1, and then, oh yeah, and then e to the negative t dt, like this, all right? So this is what we have, I believe. Let's see, yes, good. All right, so gamma of 1. In fact, this is how you can argue that this is 0 factorial. How you can argue 0 factorial should be 1. You can put on 1 right here. This is integral from 0 to infinity, t to the 1 minus 1 power. So that would be 0 actually. And then you do e to the negative t's power, dt. And you can do this in your head, integrating e to the negative t, because this is just 1 anyway. And then you get negative e to the negative t. Plug in infinity, plug in 0, work that out, you actually end up with just 1. So this right here is nicely equal to 1. Right? And in fact, that's 0 factorial. Now, let's look at the gamma prime of r. So to do that, I will actually have to do the derivative right here. And again, we will technically have to differentiate this with respect to r. So use the Leibniz rule, right? So we actually end up with the following. So let's actually write down right here. So gamma prime of r equals. Okay, still have the integral going from 0 to infinity. This right here stays because t is just a constant in the r world. We are doing this with respect to r. So you have this. And we did that earlier. So if you differentiate that, you actually get this repeat, which is t to the r minus 1 times ln t. You actually have this. And then you have this right here stays, which is e to the negative t dt, like this, right? So if you have the gamma prime of 1 when r is equal to 1, you will end up with the following. Put a 1 in here, t to the 0 is just 1, so it's nothing there, and you actually get the integral from 0 to infinity. I'm so sorry. Gamma prime of 1. This right here is the integral going from 0 to infinity. This right here is just t to the 0, which is 1, and you end up with ln t times e to the negative t dt. And do you guys want to know what the answer to this is? This right here is so cool. This is also called the gamma. This is the Euler's constant gamma, right? And let me just tell you, this is approximately 0.577. And in fact, I'm not going to do this integral right here for you guys. I'm sorry. But, of course, you guys can go ahead and check out Dr. Payan. Check out Dr. Payan's video. I will have this video in the description for your convenience. So, although this right here is actually a special number called the gamma, if you haven't seen that before. Very cool stuff. So right here, I will actually come here and tell you this right here is equal to gamma, like that. Very, very good stuff. Right? And that's pretty much it, but I'm afraid I'm making a small sign mistake. Let's see. No, this is okay. I should have a Hold on. This right here should be negative gamma or gamma. Let's see. See, this is what I have to look at Dr. Payan's video sometimes. All right, let's see if it makes sense. If you have 0, this is negative infinity times 1, so it's negative. And then when it's infinity, that's 0. So when t is 1, that will be 0. So you have negative part, and then you have some not so big positive part. So I believe this right here should be negative gamma. Otherwise, it won't work. So it has to be negative gamma. Let me just double check to see if I have any mistakes or not. Yes, I really believe this right here should be a negative gamma. Negative gamma. Can we see okay? So this negative gamma is just like a constant, just like pi or the e, right? Euler's constant. Yeah. And I will come back here and then I'll tell you this is negative gamma. Right? Finally, ladies and gentlemen, as you can see, the left-hand side is equal to the right-hand side, obviously. But of course, we have the s, and s. We can cancel them out. So you can see that on the top, you have negative gamma minus 1 over, cancel that out. So you have s like that. Oh, one more thing I forgot. I'm so sorry. I'm very sorry. All right, so you have all this. Do the derivative, right? Let's do the derivative, okay? Quotient rule, the bottom function square, and the top is the bottom function times the derivative of the top, minus the top function times the derivative of the bottom. Derivative of s to the r plus 1 with respect to r is s r plus 1 times ln s. Times ln s. Why? Is that what we did earlier? That's just like what we did earlier. So in fact, I'm sorry, this right here, we should have another ln s. After that, ln s. Right? So I'm missing that ln s. But anyway, the rest is okay right here. And again, this s, that s, and that s squared can reduce. You finally get negative gamma minus 1 ln s. So it's minus ln s all over s, like that. Whew! So already done. Negative gamma minus ln s all over s, like this. Done. Done. So done. Yes, not so bad. All right, so this right here is it. 24 Laplace transforms for you guys, right? So that's pretty much it. And in fact, I will have to ask you guys the following though. So perhaps I'll just ask you guys this. So I'll leave this to you guys. Question for you guys. This is again the honorable mention. Question: what's the Laplace transform of 1 minus cosine t over t? Right? What's the Laplace transform of that? And then after this, can you also find me the integral going from 0 to infinity of 1 minus cosine t over t e to the t dt? All right? So please do that, and let's see if you guys can get what it is and all the stuff. And hopefully this right here is really negative gamma, and if so, that would be great. All right, so that's it, and hopefully you guys all like this. And by the way, I should say s is greater than 0 somewhere. S is greater than 0, but it's because of this. Otherwise, it won't converge. But anyway. So anyway, this right here is it. And as usual, I would like to put on my marathon medal. This is the one that I got from 2017. This right here has the both sides, and it's by Sketcher. So let me just put this up. And my hand is dirty, very dirty. Dirty algebra a lot and dirty calculus. No, the algebra is not dirty. Right. Okay, so, man, feels so good every time I put on my medal. So that's it. Hopefully you guys find this video to be helpful, and yeah, let me know how you guys are doing all the stuff. Wish you guys the best. Wish you guys safe and healthy, right? So, as always, that's it.